I mean, because when you're home, you still have all your responsibilities of being home.
Yeah.
And you also don't really change. See, I still have to teach my classes and everything. And
Well, I have to feed my chickens and my dogs.
yeah, I've still got 3 kids at home.
Yeah.
So I think I'm going to receive here everyone's personal descriptions. There's Surya. No, where's Surya? We have a change in the schedule relative to the original. I think Narendra is speaking. Let's see.
Yeah, it updated. Let me just see. Updated thing we are putting in our website. Yeah. 24. Today 24. Yeah.
I was terrified that I was going to log in at the wrong time.
Oh, yeah.
Oh.
I had it all worked out at 9 o'clock Pacific time, but it's 8 o'clock.
Yeah. The fourth talk is changed. Fourth talk, in place of Dr. D.S. Pai, it will be Dr. Narendra Tuteja.
Yep.
Yeah. Yes. That will be because of the request.
I expect that the you'll send me the other bio data for the others.
Yes.
Okay, so I've got.
Okay, I'll just send it by email to you right now. Okay.
All right.
So, Paul, it's 11 o'clock your time.
Oh, yes. I'm usually going to sleep right around 10. I wouldn't dare take some coffee this time, though.
Oh, no.
Or anything like that.
This is tea.
Yeah, so my email is open.
Okay.
Sending it into the chat works too. If you just send them one by one as they come.
Okay. So first one is who's I'm just sending it. Take 1 minute.
I'm just getting the quick. There's Ashrat Raghavendra. Shows. Okay. Cool. I think we still don't have all of our speakers.
Your address PAUL. I got it.
Roundy@albany.edu, but I'm also Paul PAUL here. Yes.
I have just sent the first speaker bio. Okay.
Okay, so I can start with Peter.
Yeah. I will just introduce you. Then you will start. Okay. I have sent it. First one. Did you get it?
So, can I share my screen at some stage? Okay, yeah.
Did you? Yeah, I have sent it by mail. Oh.
Okay, I think it just came in. So just let me get a hold of it here and oh yes. So I have Peter's PowerPoint here in addition, but Peter, you can show your screen.
Yeah, okay. So should we start now? Yeah.
Okay, let me work out how to share a screen. I see. Okay, yeah.
So once you share your screen, I'll read your bio and we'll give you an extra minute on the other side.
Okay, so let us start it, I think.
Okay. So
I'll just.
Can you see my screen?
Yes, go ahead and share your screen. And
can you see it now?
I'll read your bio.
All right.
So good morning. So today, the third day of our IWM-7 workshop. Now we have a invited speaker. 4 speakers are there. So now may I request Professor Paul E. Roundy to chair the session. He is a professor in the Department of Atmospheric and Environmental Sciences at the University of Albany in New York. He holds a PhD in meteorology from Penn State University from 2003 and a Bachelor of Science in Physics. He enjoys studying the dynamics of the tropical atmosphere and its connections to the global atmosphere and ocean, specializing in analysis of large datasets in the context of the equation of motion. Over to Paul Roundy, sir. Yeah.
Thank you. Happy to be here. So this is our first speaker is Peter John Webster, is currently Emeritus Professor of Earth and Atmospheric Sciences at the Georgia Institute of Technology in the United States. His main interests are in the physics of low-frequency atmospheric and oceanic dynamics, and special interest in the structure and variability of the monsoon. His interest in monsoons stems from his involvement in the monsoon experiment, 1979 to 80, following his graduation from MIT and subsequent tropical field investigations, EMEX, Toga Core, Jasmine, that he helped design, organize, and take part in the analysis of data. Webster's overriding interest has been in the advancement of science with the purpose of applying research results for the betterment of society, especially in the developing world. During the last decade, he has led efforts for the extended forecasts on floods in the Ganges, Brahmaputra and Indus River systems, and heat wave forecasts in India. These forecasts aimed at extreme events were constructed in probabilistic form, and they're aimed at extreme events and were constructed in probabilistic form to allow users to make informed decisions and to take mitigatory actions if necessary. More recently, he has concentrated in creating probabilistic forecasts for agricultural societies, especially in rain-fed areas of the planet, and the belief that useful forecasts delivered in understandable form will improve sustainability. Webster has written many papers on themes listed above and has recently published a book on the dynamics of tropical atmosphere and oceans. He's been recognized by a number of national and international prizes and awards. I will stop my video and so Peter can begin.
Okay, I have my screen sharing. Is that working?
Not yet.
I'm not seeing it yet.
What do I do?
Otherwise, we can share from our end if it's problem.
You can't see it from your end.
No, we can't see.
Cannot see it.
Oh. Well, I'm not quite sure what to do. I guess
we can share from our end. Your PPT here, I think. Yeah.
Okay, I guess from your end, I suppose. Yeah. What to do?
Now it is shared.
Hmm?
Yeah, it is shared now. Can you see?
Yes.
You can see my screen?
We can see your presentation.
Who has shared from our end, or you have shared this screen? PowerPoint.
We have shared from our end.
Yeah, so this is now it is shared from our end. So please, you will click one by one. So you go ahead with your talk.
Can you see that's the next slide, right?
This is the first slide, so we can go to the next slide, right?
I'm sorry, I'm having trouble understanding.
So as per instructions, we will move to the slides.
Next slide.
Okay, then go to the next slide, I guess. So I'm going to I'm afraid you're missing half my stuff, but never mind. Okay. Can you hear me? Shall I start or give in or do what? Okay. I'm going to talk about monsoon prediction across a number of scales and see if there's any progress, what are the horizons, and what utility you might have from those. Next slide, please. No, I'll try. Can you see the next slide?
There we go.
Hello? I'm becoming very confused. Are you seeing number 2 slide?
Is it number?
Yes.
This is number 2.
Living in a world of variable weather and climate change. Can you see that?
Yes.
Yeah.
Okay,
Yes.
yeah. So I came across this.
Peter, you will stop sharing, then these people are sharing actually.
Yeah, you don't
can't
share.
hear me? This is a shambles, guys. I'm sorry. I've no idea what to do. I've got your picture on my screen. You don't hear me. I can't do anything.
Can hear you.
We can hear you.
Can't hear me?
Yes, we can hear you and we can see the slide.
Okay.
Just
I
tell
came,
them when to move forward.
I came across this amazing quote by Silver. It says that one can prepare, one can strive, one can make a choice, but ultimately life is an elaborate game of providence and probability. So providence is normally a religious thing, but let's consider it to be nature. The providence can give you demonic or benevolent behavior. And what we need to do from that is determine the probability of adverse or clement weather and the occurrence of hazards, when, where, what amplitude, and what duration, and convey this information to users in a manner that is useful. But having said that, we have to ask, can we produce forecasts that are fit for purpose? And I'll explain later on what fit for purpose means. Are they useful forecasts? Next slide, please. No. Can you see my third slide?
Yes.
So one of the problems we have is that we've broached this thing called the valley of death, where new methodologies, results, and good intentions often perish. We have, on one side, people producing basic research, innovation, and so on. On the other side, we have users who want to use a forecast, but quite often the two don't meet. So somehow we have to keep the innovations from falling into this peculiar valley of death. Next slide, please. So it's normally we think in terms of prediction, in terms of a hazard perspective, how bad are things going to be? But really, we have to consider the full gamut of weather. When you think that in the developing world, 68% of the uses rain-fed, non-irrigated farming practices, and globally it's about 80%. So forecasts of 1 to 15, 30 days are of critical importance, and they need to be communicated and implemented. What we know that we've showed that hazard forecasting we can do quite well, but that's not all people want to know. So the goal of usable intraseasonal forecasts remains elusive, and we need some improvement in seasonal forecasts, which I'll come back to later. Seasonal interannual forecasts are limited in accuracy and they're limited confidence or utility. Next slide, please. So what does exist is a rather haphazard overlapping multi-tiered prediction scheme. And today we have short-term forecasts, 1 to 15 days. They're in practice and they're okay. Interseasonal forecasts, 15 to 30 days. They're tactical, but possible. Seasonal forecasts, they're strategic, but lots of problems. Decadal, hey, let's talk about that later. So what we want to do is produce a forecast system that is useful, understandable, and transmittable to a user community. And this will allow us to assess, in other words, are these things fit for purpose? We look at those things in the yellow thing, are they useful for the general public? Next slide, please. So what we want to do on the top box here, we have a probability distribution of forecasts. It might be for heavy rain, 20%, and for light rain, 30%, and no rain, 10%. A user community knows what to do with those forecasts. They know when to plant, when not to plant, when to avoid hazards, and so on. So what we need to do is combine those two in order to give a forecast that combines what the farmer needs or the user needs with a probabilistic forecast to come up with a system of aggregate risk. So we have in the next slide, you might say that a viewpoint is sustainability through hazard anticipation and mitigation. And the reason we do this is for providing farmers and users information they can use right now. But we're of the belief that a society that learns to deal with present era hazards will be best equipped to adapt to and reduce the impacts of more frequent and intense hazards that may be encountered in a changing climate. By the way, the acronym for this is SHAZAM, which is onomatopoeia for rolling thunder. Next slide, please. So I'm going to give 3 examples of short-term forecasting where we stand. I'll give 1 to 14-day probabilistic precipitant forecasts for central India, flood hazards in Bangladesh and Pakistan. I'm going to introduce a new metric called the Extreme Forecast Index, which is put out routinely by ECWF. I think all probabilistic forecast producers, India, Japan, Taiwan, Bangkok, can use these. The website is down below. Next slide, please. This is a probabilistic rainfall forecast that lags 2, 5, 8, and 11 days, 14 days, based on the ECWF ensemble forecast. The map on the right-hand side, upper corner, shows you the area that we've chosen. The first graph is a rainfall observed from June the 17th, which turned out to be the onset of the monsoon, all the way through to August. And below, you can see the forecast for lag of 2 days, 5 days, 8 days, 11 days, and 14 days. And as you look down, the 2-day forecast, the 5, 8, 11, and 14 all pick up the peaks. They also pick up the valleys. So the forecasting system at all the way out to 14 days is picking up the periods of no rain and picking up the periods of maximum rain. Now, this is just a raw forecast. They haven't been calibrated using statistical techniques that we normally use. So I can say that we can forecast quite well and tell a user that there's a high probability or a low probability out to 14 days of a dry period, for example, or a peak in precipitation. So this is, I think, useful information. This forecast fits the purpose of allowing a user to be able to decide on what he or she wants to do. Next slide, please. These are the 14-day, 10-day forecasts we did for using the ECWF ensemble forecast for the Brahmaputra. And we've done this for many years now. And what it shows, this is the dashed line, horizontal line, is the flood level. And you can see that we have a swath of ensembles around the black line, which is observed. And so there's a high probability of precipitation and therefore flooding. This is also a hydrological model during this period of flooding. So this was very, very useful for the farming community in Bangladesh. It's now a routine product that we produce in conjunction with RIMES for Bangladesh. Next slide, please. Were these forecasts useful? Was the concept of probability understood by people who you might not expect? This is a meeting we had, which was a summary of the 2008 floods. And this guy is an imam from a union in Bangladesh. And he said that we disseminate the forecast information, really the flag and pillar, that they use a communication if there's going to be a flood or heavy rain. Flags are hoisted on that. They read the flag and pillar to understand the risk during prayer time. In my field, was it seedling and transplantation? So I used the flood forecast information for harvesting crops and making decisions for seedling and transplantation. Alas, also we saved household assets. And these are the savings that these flood forecasts did. rather than the flood arriving and wiping out everything, they could alter their fisheries, their agriculture, their livestock and household. There's some beautiful pictures I don't have here of livestock being moved to higher ground and that's therefore saved. Normally they were drier, so people believed the forecast that they were useful. Next, please. The Pakistan probabilistic forecast we did for 2010, 2012. You may remember that was a terrible period, 3 years of consecutive floods. So what we have in the ordinate here is the lag, and each of these is a plume of probabilistic forecasts relative to climatology. And you can see that these plumes and the observations of these blue curves here along the abscissa. And you can see that there are 10, 14-day warnings of heavy rain. And each one of those plumes finishes up with the observed blue curve along the abscissa. So I think this is showing very, very well that probabilistic short-term forecasts are doing particularly well. They're fit for purpose. Next slide, please. And also, not just rain. This is the probabilistic heat wave forecast for Ahmedabad. And they show, here we have lags on the ordinate again. This is for the temperature greater than 43 degrees C. And you can see that, again, we have these plumes relative to the blue curve, which is observations. So lots of warning. And they also picked out greater than 45 degrees on the bottom curve there. So we're doing quite well. Now this term, this EFI is the, it's a map of exceedance of climatology in the period greater than 90% of climatology, way bigger than climatology. And you can see that here in India, this is Ahmedabad here in the yellow dot, and all around it, they're expecting 5 days in advance enormously warm temperatures. So there are tools that we can use which are quite useful. Next slide, please. The Yucatan flooding, June 13th. On the left-hand side is the plume showing 8 days in advance relative to the blue curve that could have been forecast very, very well 7 days in advance. And on the right-hand side are the EFIs indicating an extreme precipitation. And you can see as we get advanced in time, 6 days, 5 days, 3 days, that Yucatan, which is the two black areas here, the two states, were warned for extreme precipitation. Next slide, please. So I think in terms of the 1 to 14 days, if one is prepared to think in terms of probability and communicate the probability to the user, we're doing very, very well. Less so with seasonal forecasting of the monsoon. This next slide shows the relationship of the ARI with the contemporaneous El Niños of the Oscillation Index. So when you look at below average, above average, deficient or heavy, it shows that most deficient El Niños are associated with El Niño, and most heavy, greater than 1 standard deviation over the All India Rainfall Index, which is all of India, it's occurring with 7. So the trouble is, that's a contemporaneous El Niño. When you look at the rainfall and then you check the contemporaneous, and so you find that there's a strong relationship. The trouble is, do we know what El Niño is going to be in advance so that we can forecast for India or wherever that is going to be a deficient rainfall? Next slide, please. This just shows you the wavelet analyses of Niño 3, SST, and ALR. And there are two things to note here. And more importantly are those spectra in the second column. And one shows a maximum of 3 to 4 years and a monsoon rainfall 2 to 3 years. It's quasi-biennial. So there's some interesting information here But the thing to note is that during the 1930s to 1960s, the original correlations of the SOI, Southern Oscillation Index, and the Indian monsoon rainfall just decreased. So there was a 20-year period where there was no relationship whatsoever. This is called what I call the Norman Troop minimum. Next slide, which shows you the covariability of monsoon and ENSO. And the correlation is strong, but it's now over a much broader period, 2 to 8 years, rather than the 2 to 3 years. But, you know, the interesting thing about the monsoon spectra, there's a strong biennial oscillation. And where does that come from? It'll give us a big clue of what has happened. Next, please. One of the problems was that when you know the SOI in June, July, and August, it correlates with the SOI in the next December, January, February at about 0.8. That's very strong. However, the December, January, February SOI is a zero correlation with the June, July, August. And of course, the SOI for June, July, August is the thing we want because that tells us if the monsoon is going to be strong or weak. The graph on the right-hand side shows this demise of correlations as you move through. And there's no correlation between what's happening in the one side of spring and the other side of spring. And this is sort of devastating in a sense, because it means that if you know what the SOI is, you get a good forecast, but if you don't know it in advance, you have no forecast. Next slide, please. And these are regression analyses, and a bit difficult to without a long explanation. But this is a regression of the November, December, January Nino 3 onto the SOT and the ARI. What it shows is that weak monsoon occurs 4 months prior to the Nino 3 SOT maximum. Noticing that before, that table I showed a contemporaneous. So in other words, we're not getting much information from the contemporaneous SOI. And this is a regression of a Nino 3 on the ARI, and the maximum strong monsoon occurs 4 months before the Nino maximum. So in other words, what we're seeing, in a sense, is that the regression analysis tends to support the conclusions of Norman, which is that the monsoon is more of a broadcaster rather than something that is the result of ENSO. So the question might be, is the variability of the monsoon causing variability of ENSO? This is an interesting thing because
we need to start wrapping up.
Oh my God, already? I've only been out about 10 seconds. Anyhow, well, it doesn't matter. The Indian monsoon stands out as an active, not a passive feature in world weather, more of a broadcasting tool. So Walker's analysis offered promise, but for other regions rather than India. If I've only got a tiny, this is why we don't see any correlations. It's by a guy called Hofstadler. So let's forget that. So what I'm going to suggest is that we have a riddle, which is the ENSO monsoon pretzel. And we're not quite sure where the pretzel starts and where it finishes. But monsoon and ENSO are indelibly connected. So it's not just a simple idea of if we know ENSO, we know the monsoon, or if we know the monsoon, we know ENSO. It's rather complicated. All right, so, and also, and I'll end at this, if we knew perfectly what we had a perfect ARI forecast, do we know the regional seasonal monsoon? Can we tell somebody in Uttar Pradesh that's going to be a weak monsoon, therefore you'll have stronger weak? And these are just a number of years. These top ones are for very strong monsoons, the bottom ones are weak monsoons. What you see is a patchwork of above average and below average. And so knowing that the monsoon is going to be strong doesn't tell you that central India is going to have way, way below. So we need to think of different ways of forecasting the monsoon. Am I out of time? Because
I think what we can do for questions is put them in, they can put them in the chat, and you should go down and read the bottom of the chat so you can respond to any questions that come in, so
yeah,
we can move forward.
yeah.
And I'll shorten my talk just a little bit, and I think we can try to, I think the last part can go a little bit later.
Yeah. Anyhow, why do we have strong and weak monsoons? And it's not because of ENSO, it's because of the Indian Ocean. And one of the things about the Indian Ocean is that the transport of heat by the ocean and transport of heat by the atmosphere are completely out of phase. And the interesting thing to notice at time, I would tell you that the transport of the Indian Ocean precedes a strong and weak monsoon. So finally, these are the annual anomalies of meridional heat transport on the top right. And you can see every 2 years we get strong northward, strong southward, strong northward, strong southward. And so this leads us to why we get strong and weak monsoons. And it's next 2 slides, and I'll stop here. So a strong and weak monsoon, a strong monsoon will cause you a strong southward transport of heat by the oceans, by Egmont transports. A weak monsoon will be weak, so you oscillate back and forward biennially, and this impacts the monsoon precipitation completely. So you can't forecast the monsoon by considering ENSO alone. You have to take into account the other aspects of the Indian Ocean. Becomes enormously important. So that's about it. I've
Interesting, Peter. Yeah, so anyone with questions, put them in the chat, and so Peter can respond to you there, and we have to move on. When I hope to be able to talk to you about some of this, actually. It won't happen today, but I'd like to visit with you about it.
There is
Very
a question
interesting.
in the chat box. There is a question in the chat box.
I'm sorry?
There is a question in the chat box to Dr. Peter. Can I read it?
Peter can't understand you. I'm sorry.
There is a question for you.
So you can find your questions in the chat and respond to them privately there. So I can begin
Sure.
my talk.
Okay. Yeah.
I'm going to try to wrap up before 11:40. I'm looking at my time, but 15 minutes from now.
Okay. Thank you, Paul. Yeah. Anyhow, anybody, they can view my my presentation if they want. They have access to that, don't they?
Okay. Can everyone see my presentation?
Yes, we can see.
Okay. So we're looking at subseasonal variability associated with the monsoon, the connection between that subseasonal variability and the extratropics, and considering both equatorial Rossby waves and the Madden-Julian oscillation. So it's broadly known, I think, in this group that the MJO and other subseasonal modulations impact eastward and poleward propagating break and active periods in monsoon regions. We also have seasonally modified equatorial Rossby waves that modulate westward and poleward moving break and active regions. And these equatorial Rossby waves and the MJO can correlate with each other as well as have independent variants. Extratropical Rossby wave breaking is a major player relevant to both the impacts of the MJO and the equatorial Rossby waves on monsoons. Now, get this thing out of the way here. So we're mostly familiar, I think, with Ginn and Hoskins' result where they put a heat source here on the dateline along the equator, and it produces this overturning circulation in the zonal wind along the equator. And in addition to that, there is, let's see if I can get back here. So yes, in addition to that, the heat source produces a barotropic Rossby wave response that radiates around, especially through the winter hemisphere. In this case, the northern hemisphere is considered the winter, and a wave train also extending into the summer hemisphere. For the illustration I'm going to show you just now, we're going to focus on northern winter, and then we'll move on to northern summer events. We're going to identify MJO events that include Central Pacific Rossby wave breaking near Hawaii when MJO convection is over the Eastern Indian Ocean. And we're going to compare the progression of events, of those MJO events that have the Rossby wave breaking near Hawaii and the events that don't. This is from McCritchie and Roundy 2016. In order to get the background understanding we're looking for here, I'm showing you a map of potential temperature on the tropopause during northern winter. We can see where the subtropical jet comes through here in the northern periphery of this high potential temperature region of the tropics. And then the Rossby waves that propagate around the world will propagate linearly in the regions of strong gradients, and then they will break. So you a region of strong gradients right here, east of Asia and east of North America. But then as the waves propagate farther to the east, the gradient weakens, and it is in these regions where the waves tend to break. So you imagine MJO convection here yields a response on the jet and then breaking waves downstream. And here is figure 9 from Moore et al. 2010, showing how the MJO induces anticyclonic and cyclonic Rossby wave breaking. We have here in the top figure MJO over the Eastern Indian Ocean, acceleration on the jet, and wave breaking through the Central Pacific, initiating convection in the equatorial region here. As the convection progresses over the Pacific, the Rossby wave breaking extends to the east as the jet extends, with wave breaking into the tropics relevant to convection of the East Pacific at that time. And this is also a mechanism whereby potential vorticity tails drop into the tropics and break off and become equatorial Rossby waves that then propagate to the west. So here is from McCritchie and Roundy 2016 from the Quarterly Journal, showing two different MJO conditions with active convection shown in the blue shades over the Eastern Indian Ocean here and here, with the suppressed convection at the same time over the Western Pacific. The MJO convection leads to a Rossby wave response downstream and a ridge over the North Pacific. Advection around the ridge here brings high potential vorticity air from the extratropics down, breaks off these cutoff cyclones that become the cyclonic gyres associated with the MJO, or they reinforce those cyclonic gyres. While the events that don't have Rossby wave breaking near Hawaii lack the same gyre pattern. So I'm going to reconstruct for you a set of generalized northern summer and northern winter, northern summer MJO and northern winter equatorial Rossby wave cycles. We're going to follow the result from, or the method of Roundy 2017, which is the method of seasonally varying regression slope coefficients. This method allows us to diagnose global atmospheric circulation patterns associated with MJO indices as a continuous function of the seasonal cycle. So you can diagnose the relationship between the MJO and the tropics and signals in any part of the world as a continuous function of the seasonal cycle. The results here for the MJO are based on the RMM index of Wheeler and Hendon. And for the equatorial Rossby wave, we're looking at the first two principal components of Rossby filtered outgoing long-wave radiation anomaly. So this is the, we'll call it the phase 1, just moving to the Indian Ocean, active phase of the MJO centered around August 9th. And we see active convection in the blue shade stretched across the Western Hemisphere and amplifying over the Eastern Indian Ocean, with suppressed convection over here moving northward and eastward over Southeast Asia and the Western Pacific, correlated with this geopotential height anomaly pattern across the Northern Hemisphere. And we're going to march forward through this, watching the convection march poleward and eastward. And at the same time, I don't have enough time to go back to the ones I was going to show here, but let's just look at this ridge pattern over northeastern Asia. Leading up to this pattern was a stronger ridge farther to the north, bringing down high potential vorticity air and dropping the cutoff cyclone into the tropics here, forming a block. And this trough modulates the outflow from the convection here across Southeast Asia and the Northwestern Pacific. And then the convection continues northward and finally damps out. Now, Wang and Shi in 1997 in Journal of Atmospheric Sciences showed one mechanism of the Northern Hemisphere summer MJO is eastward propagation of the MJO convection along the equator, and then with equatorial Rossby waves shed westward from the Pacific MJO, then impacting the Southern Asian monsoon. I'm also going to show that such equatorial Rossby waves can also emerge due to tropical extratropical interaction. So this is our equatorial Rossby wave theoretical pattern. We have a pair of twin ridges and twin troughs. The poleward advection of low potential vorticity air here west of the ridges leads to spinning up the ridges to the west of the present centers, and you get westward propagation as a Rossby wave. Now, we're looking at a northern winter equatorial Rossby wave signal. You can see associated with it the twin ridges and troughs near the maritime continent and Southeast Asia. But the key information I want to look at first is this ridge over the Northeast Pacific. This ridge, Rossby wave breaking around this ridge, brings these cutoff cyclones into the tropics here. And this then backs to the west and develops as the equatorial Rossby wave train that then approaches the Indian Ocean. So the principal source here is very interesting. You can have convection over the Indian Ocean here, yielding a wave train response that builds the ridge over the North Pacific, and then that same ridge over the North Pacific drops the troughs on its equatorward side due to Rossby wave breaking. Now, during northern summer, it's somewhat different. I want to focus first on the convection, looking here over the Eastern Indian Ocean and Southeast Asia, and then we'll look over the East Pacific again for the precursor patterns. So marching forward, phase 1, 2, 3, 4, we see these westward and northward moving active region over the Indian Ocean moving into India, centered around the 30th of June. Notice there is a little bit of symmetry in the convective features here over the Pacific, but these features are more centered in the Northern Hemisphere, just like Ben Wang had previously shown. Backing up again, when the convection associated with the Rossby wave is over the Indian Ocean here, there is a ridge over the Northeast Pacific, which draws down, as I described before, the high potential vorticity air, organizing the trough on its equatorward side, which then organizes and propagates westward. You can see it here. It moved all the way around the ridge and then propagates farther westward over southern Asia. And this is, again, similar to this original paper from Ben Wang. The active convection moving eastward along the equator, and then by their assessment, backing to the west from here. And I'm also seeing a center of action beginning over the Eastern Indian Ocean and moving northward and westward associated with this westward moving feature. And I assert that a principal cause of the observed westward moving waves here is wave breaking from the extratropics. So my conclusions are the MJO and equatorial Rossby waves interact with extratropical Rossby wave breaking. A portion of eastward and northward components of the northern summer monsoon system's break and active cycles associate with the MJO, and westward and northward moving features associate with seasonally modified equatorial Rossby wave signals initiated by extratropical Rossby wave breaking. And so I can say we have just a couple more minutes. If I was supposed to be finishing at 11:40, so we're shifting back just a couple minutes. If there are one question or two questions. If I stop my share, I think I'll be able to see the chat. So I'm going to say stop sharing.
Hey,
Okay.
Paul,
Yes, please.
it's Peter. I have a slightly different interpretation of what produces the wave breaking.
Sure.
And I'll in terms of potential vorticity transports, of course, the monsoon transport potential vorticity north produces the net jet stream at about 30, 40 degrees south.
Yes.
That becomes unstable as into a region of negative stretching deformation, waves break, and they come back towards the equator, and then they influence the monsoon. So you get a nice cycle. I'll send you a couple of chapters from my book, which might
Sure.
explain that. So I'm doing that right now.
Okay. So I'm going to introduce the next speaker. Dr. Surya Chandra Rao. And you're welcome to begin showing your screen. Dr. Rao is a senior scientist at the Indian Institute of Tropical Meteorology and is leading Monsoon Mission Program of India as Associate Mission Director. Monsoon Mission is an ambitious mission mode program to improve the skill of Indian summer monsoon weather and climate. As a result of this program, India's dynamical model are now one of the better models among models from other leading centers. His work on Indian Ocean dipole, Indian Ocean warming, and Indian Ocean monsoon variability and prediction were highly cited by peers. Dr. Rao has published around 100 research papers with high citations around 7,000, impressive, and leading international journals and received several awards nationally and internationally. At present, he is also serving as a member of the Clivar GWAX Monsoons panel. His efforts as project director of high performance computing is also responsible for establishing India's first multi-petaflops high performance computer. You're welcome to go into presentation mode.
Yeah, thank you, Paul. Good morning to everyone, and for someone, good evening, and others, good afternoon. So today I will be talking about SST friends in the Bay of Bengal and the Bay of Bengal, its impact on Indian summer monsoon rainfall. So there will be so many collaborators in this work, and some of the works have been already published. Some of them are communicated, and some of them are under progress. So we know that Western boundary currents play a very important role in control the climate. As the good examples are Gulf Stream and Croatia extension and Croatia currents. So when it comes to Indian Ocean, particularly North Indian Ocean, it is landlocked. So normally these Western boundary currents that when we talk about in Atlantic and Pacific, they move all the way from equator to mid latitudes and to polar regions as well. Whereas in Indian Ocean, the land is locked on the northern side. The Indian Ocean is locked by lands in the northern side. And at the same time, the current speeds of these western boundary currents, the Somalia and East India coastal current, their speeds are much lower compared to the speeds of this Gulf Stream and Croatia currents. So they're almost 5 times less speed in Indian Ocean. some background noise is there. I think someone's mic is on. Yeah. So it is interesting to see whether such weak currents in the Indian Ocean can have any impact on the climate, particularly on the monsoon. That is what is today's talk is about. So if you look at Gulf Stream, Minobe et al. 2008 have published that if you smooth out these SST fronts in the Gulf Stream region, the rainfall simulated by AGCM is much smoother, and you don't get such strong rain rates that you normally observe. So that means it clearly indicates that the SST front in the Gulf Stream region is significantly impacting monsoon, the rainfall over that region. Similarly, for Kuroshio region also, it modulates the, this is a study by Yoshida et al. The latitude plus Kuroshio and its extension enhance explosive cyclones and cause local and basin scale atmospheric response to the SST front. So both Gulf Stream and Kuroshio have shown that there are many studies which have shown that it strongly impacts either the storm track in Pacific and Atlantic. So what happens in the Indian Ocean when we are trying to look at things which are changing seasonally as well? So that is the basis of this today's talk. And Bay of Bengal, if you look at this is the Bay of Bengal SST and sea level anomalies. So both are shown here. They both shows that very strong, rich eddy activity in both the fields, both in sea level anomalies and also SSTs. So today's talk is trying to understand how these fronts in SST and these eddies will impact Indian monsoon. Okay, so this is another slide from Chennai et al. 2018, which shows the eddy kinetic energy centers in the Bay of Bengal. You can see that there are 3 regions where the eddy kinetic energy is much stronger. Most importantly, we are concentrating on the western side of the Bay of Bengal. And this eddy structure is mainly due to the coastal trapped Kelvin waves traveling along the periphery of Bay of Bengal. So one of the major rain-bearing systems in the Bay of Bengal during monsoon season are low-pressure systems. So if you look at a composite of and the background state of this Bay of Bengal during when these things are forming, when low-pressure systems are forming, what you notice is that this is the mixed layer depth, and this is SST, this is sea surface salinity fields in the Bay of Bengal. So what you notice is that there is a strong front that is seen very clearly both in SST, mixed layer depth, and also in the sea surface salinity. So it is very encouraging to assume that these fronts will play important role. So we will see how these fronts will play important role in controlling or modulating these low pressure systems. So what is required for formation of low pressure systems in the Bay of Bengal is humid and convective unstable environment with high cyclone participity and high sea surface temperature. That is what is most important. So all these fields are there, but one thing that it's not, if these fronts are not available, not there in the Bay of Bengal, what happens to these low pressure systems? That is what we will look at it. See, in India, we have been using CFS coupled model for making forecasts and extended range and seasonal range time scales, and the atmosphere component we are using it for making short range forecasts. One of the these are the SSTs in a low resolution model and high resolution bias of this, and the difference between low resolution and high resolution, and these are the rainfall biases. So one noticeable thing that you notice over India is that almost all coupled models, including CFS, shows very strong dry bias over Indian landmass region. So that is the one of the problems that almost all coupled models face today. So is this SST front has any role in controlling this? That is what we'll look at it in the following slides. So what we did is we did some sensitivity experiments using CFS model. It's simply what we did is that we just removed ocean dynamics by prescribing a slab in different regions. Ice slab means in ocean, there are no ocean dynamics, only slab model is there, and the SST is calculated using simple bulk formulas. And P slab, first week, the no ocean dynamics are there in this run, and in the control, all ocean dynamics are there. These are the observed climatology of SST and rainfall. As I told you earlier, in the control, you see very clearly strong dry bias over Indian land region and cold SSTs in the Northern Indian Ocean region. When we somehow cut off the ocean dynamics, this dry bias over Indian land mass improves, means it decreases compared to the control run. And what we have noticed is that there is some structure that is coming very clearly in the Bay of Bengal is the warm SSTs are popping up very clearly. Whereas in P slab, the dry bias increases because you have a perennial like El Nino in the first week, and SSTs are cooler along the this SST front. That is what is the reason. So the one thing that we have understood from these experiments is that if you have a warm SSTs in the Northern Indian Ocean and some gradients are maintained, then definitely the prediction skill of these models will be as good as control run, even though there are no ocean dynamics. So not much of ocean dynamics is playing a role, but the important thing is that the SSTs, which are very close to observations, are important for giving that same internal variability. Whereas if you don't have P slab, that is, there's no Pacific dynamics, the scale drops significantly to 0.14. Whereas between control and ice slab, you don't see much of difference. However, the internal variability drops significantly in the ice slab run. So this experiment has given confidence that yes, SSTs in the Bay of Bengal are very important for modulating the monsoon. So then we try to look at whether what is the reason for having a strong dry bias over Indian land region. So we look at the low pressure systems in the coupled model, and what we notice is that in the control run, these low pressure systems don't propagate much deeper into the Indian land mass. So that's why you have a strong dry bias in the coupled model in the control run. Whereas in ice slab, because you have the SST gradients very clearly, so these low pressure systems propagate deeper into the Indian landmass and gives you more rainfall, and therefore the dry bias has reduced significantly. Whereas in P slab, they don't even move to the Indian land region. If here I am showing you the different fields of humidity in different RH and Q in different runs, what you notice in reanalysis is that there is a strong humidity front, not only SST front, even a humidity front is hugging the coast of Bengal, east, western coast. So whereas that is not seen in the control run, whereas ice slab, you get some signal, in P slab, you don't get it. So again, getting this humidity front is another important thing for getting the low pressure systems properly in the models. And it appears, not it appears now, it is, we are confident that without having this front of SST, sea surface salinity, and MLDs, we will not be able to get low pressure systems in the coupled model significantly propagating deep into the Indian land region. So Hirata et al. Have done a very good experiments by controlling latent heat flux and sensible heat flux in the Gulf Stream region. And what they noticed is that they have used CERES model, the cloud resolving storm simulator. And what they have noticed that when you suppress this latent heat flux and sensible heat flux in this region, the storm track moves away from the Gulf Stream region. So that is what is one thing they have noticed. And similarly, they have done a similar experiment in the Bay of Bengal, but unfortunately, they have considered the whole of Bay of Bengal to do the experiment. If they have restricted their region only to the western Bay of Bengal, then things would have been different. Again, they come to the same conclusion: if there is no latent heat flux and sensible heat flux from the Bay of Bengal, the low pressure systems that are forming, the rapid development will not be there in the Bay of Bengal as well. So we have done an experiment using WRF model by giving mixed layer depth modulating the mixed layer depth and SSTs in those regions. And what we have noticed is simply is that if this SST gradient is not there, the number of low pressure systems forming are very, very few in the Bay of Bengal. So once this downscaled high resolution WRF model coupled with a slab ocean model is used, so we are able to get that SST front in the Bay of Bengal very clearly. So that is making us confident that the SST front in the Bay of Bengal is very much important to get mean monsoon circulation correctly and the low pressure systems also correctly. Not only that, even the PDF of the rainfall in different regions, Bay of Bengal, Central India, and Arabian Sea and Equatorial Ocean improves significantly, particularly our Bay of Bengal and Central India improves significantly because of the SST front is simulated very well the model. And the skill also improves in the model when you have that SST front in the Bay of Bengal. So now we started looking at whether the SST front alone or the eddies which are prominent in the Bay of Bengal are causing this. So this is, we have used Okubo V's parameter to identify the eddy structure in the Bay of Bengal, and this is the OWJJ index. And you can see that the Western Bay of Bengal is very rich in eddy structure, and this is the time series of that. If I take a time series of anticyclonic index, eddy index, and correlate with rainfall everywhere, what I notice is that the rainfall over Indian region is significantly enhanced. So whenever I have a strong anticyclonic activity in the Western Bay of Bengal, the monsoon is getting strengthened along the Western Ghats and also in the Central Indian region. So that is very interesting result. And whereas when you have cyclonic eddies in the same region, the monsoon rainfall decreases. Similarly, when the anticyclonic eddies are on the away from the west or the east, then also the monsoon rainfall decreases. So we found a very strong correlation between this eddy structure that is happening in the Bay of Bengal, particularly in the Western Bay of Bengal. So to conclude that, what we have done is we have done two experiments. One is with control SST and SST smooth. These are the two. This is the smooth one and this is the control where the exact SSTs are given. The difference is here. You can see that the eddy structure is very strongly there in this Bay of Bengal. So those eddies are removed. Once you remove those eddies, what will happen? So what we have done is that we have used GFS version 14 semi-Lagrangian model with 0.125 degrees resolution with 64 vertical levels and selected 2 years. One is 2018 and another is 2019. So wherein the East anticyclone index is stronger in 2018 and West anticyclone is stronger in 2019. So as noticed earlier in 2019, when the Western anticyclones are there we have noticed the decreased rainfall, and when Eastern, so this is opposite, sorry. So when you have a Western anticyclones are stronger, then the rainfall has increased. When the Eastern anticyclones are there, rainfall has decreased. So then we try to understand why this is happening. So in fact, these eddies are modulating the wind speeds and the advection and convergence, and therefore what we have noticed is that when we carried out the master budget analysis, what we noticed is that in the both smooth and control runs, the difference observed in the precipitation was contributed dominantly by the convergence term and also followed by the advection. So these two terms are contributing to change in the rainfall over Indian region. To summarize, so SST, MELD and SST front along the east coast of India is an essential component of monsoon, and for formation of low pressure systems, it is very much required. And eddies in the Bay of Bengal are definitely modulating the advection and convergence of master budget significantly, thereby influencing the seasonal wind monsoon. So Western Bay of Bengal anticyclones tend to increase monsoon rainfall, whereas Eastern Bay of Bengal anticyclones decrease. So other way is that if their cyclonic eddies are there, then they also try to decrease the rainfall there. So now the questions remains is that how well, since all these models that we are using for seasonal forecasting, they are coarse resolution. At the maximum, we can go up to 38 kilometers at this moment. So how do we get this eddy structure correctly in these models? That is one of the questions that will be the future study. And how do we parameterize this reactivity into these models, and how well we can represent the SS different. Why the SS different is so important for low pressure systems to form, and what other mechanisms are driving that. So with that, I conclude my thank you.
Thank you, Surya.
Yeah, thank you.
We're still running a couple minutes late. But I think we've all pushed back a little bit. We're welcome one quick question, or put your questions into the chat so he can respond to you there. Okay, so we can introduce our final speaker. Looks like there are new messages coming in, so Surya, just check down there for your questions.
Yeah, I'm asking them. Thank you.
All right. Okay, so let me find my way back. Just one moment. Okay, Dr. Narendra Tuteja has over 30 years of scientific and engineering experience in industry, applied research, and academia in hydrology, water resources, and natural resource management across Australia, Europe, and South Asia. Narendra has supported development of policies and decision-making in the water sector. He has guided development and delivery of operational water quality and quality forecasting services at short, medium, and extended range timescales in Australia. In his current role, he guides rural water supply and flood modeling work of water in New South Wales, which was a state-owned corporation and bulk water supplier in Australia. He has collaborated nationally and overseas and published peer-reviewed literature on wide-ranging topics in water and environment domains. He is a member of the Hydrology Coordination Panel of the World Meteorological Organization, Earth System Modeling and Prediction, and author of other WMO works. I think this is missing some portion here. There we go. So you're welcome to show your screen.
Can you see my screen now?
Yes.
Okay.
And we can go through 20 or through 25 minutes after 20 minutes after we start.
Thank you. And are you seeing the screen now?
Yes.
Sir, the screen is split into two.
Okay, so
Put in the full screen instead.
yeah, just bear with me, please. Let me do it again. How about now?
Yes.
Good. So while I'm talking, I'm actually not seeing you or the other screen, so I hope you'll bear with me. Thanks very much for the introduction and the opportunity to talk about the work that's been done in Australia and I guess more internationally in cooperation with WMO partners. So I do want to acknowledge, and I won't go through all of these slides, but the contents of this slide, but I do want to draw upon a couple of things. Firstly, the work described here is largely developed within the Australian sort of community of practice, led by the Bureau of Meteorology, CSIRO, university sector, and there's also substantive work done with WMO partners. None of the work in the water industry can possibly be done without the industry partners. As you know, water users are absolutely critical, and some of those sentiments were captured in the earlier talk by Peter Webster. So, and there are a whole raft of those agencies who have been involved, and there are many colleagues on this call from IMD, IITM, NCM RWF who have been critical for, I guess, drawing upon their experience on what needs to happen in different parts of the world. So that's the outline of the talk that I'm going to go through in the next couple of minutes. So there's an overview of what work is being done on the WMO side through an initiative called Hydro SOS, which I'll talk about in a minute. As part of the WMO initiative, we've also done some evaluation about how do global models in the climate domain, and when you operate the water hydrology problem at a global scale, how does that compare with high resolution models where the local scale decisions are made? So some very sort of quantitative assessments have been done, and I'll share some of those perspectives. I'll draw upon some of the work that's been done in Australia around the development of services. I think Peter Webster touched upon this a little bit in his talk. There's a lot of work done around the globe on flood forecasting, but very little on what happens to water forecast beyond the flood time frame. So a lot of those services have been developed through the cooperative business model used in Australia, and I'll share some of those thoughts, what's been done. I'm actually going to come to the water sector needs and challenges and the pain points, and largely to use this opportunity with the climate community of practice that I see here to reflect upon that, why it is important for us to think about the partnership model, and then I'll conclude some remarks from there. So what is Hydro SOS? It stands for Global Hydrological Status and Outlook System. It's trying to do essentially moving the WMO footprint beyond the flood time frame, through which typically has been done through an initiative called FFGS, or Flood Forecasting and Guidance System. Moving to the system that actually could be owned by national meteorological and hydrological services, and delivered regionally. So what's being tried there is really something that can assemble all the data together, which is by no means unlike climatology, a very difficult task for hydrology data to be coordinated in such a cooperative way as the climate community does, for a whole raft of reasons: political, technical, bureaucratic, and what you may. So the aim is to really look at what is the current status. Is it near median, or on the dry, towards the dry end, or towards the wet end, or wetter than normal? And how bad or good it's likely to be going forward. And the time scale of interest in Hydro SOS is really down to a week for tactical operational reasons, and then to sub-seasonal kind of 30-day time scale when most of the resource assessments are done, and then for bulk water planning, thinking about somewhere in the time scale of about 3 to 6 months, and noting that the predictability and the skills go down quite drastically from there. So the Hydro SOS is not aiming to be particularly prognostic to a particular model or modeling paradigm, rather how this system could be built ground up, basically leveraging the initiatives that are underway in various regions, in various countries, and various sort of national meteorological and hydrological services. So what Hydro SOS really intends to do is bring the hydrological data into a framework which could be broadly considered in the next 5 years in a WIGOS kind of framework. Brought it into modeling paradigms that could be a synthesis of what happens in the GDPFS, and bringing hydrology into Earth system sciences, work with the community around how those products could be developed and disseminated. So there was a pilot phase. Ganga Brahmaputra Meghna Basin was one of them. and the other was Lake Victoria in Australia. That concluded last year. And then at the last Executive Council, there was an endorsement given for regional implementation in the next sort of 4 to 5 years. And then hopefully there's a lot of work to be done in this. So I think the water community and the climate community need to work together quite well over the next couple of years for if there is even 50% of what is anticipated or aspired can actually be achieved. We all know there's been a best practice guideline on seasonal climate prediction. There's actually a seasonal hydrological prediction guideline that's been in the making, and that's actually been released only yesterday. And those links are available on the WMO website. Broadly, there's a conceptual framework to this audience. I think we don't need to talk too much about what's the essential building blocks. But one thing I do want to point out, there's a need for us to recognize that there are high resolution models that can be based upon a framework presented here. There's also a belief in parts of the climate community that why can't we use directly the climate models and bring them into hydrology domain. So the question then is really, can we use them directly, or we do need to have some additional built functionalities in the local system that we can work together. And the idea should be somehow we do a verification at the hydrologic scale at those lead times that we're talking about. So that brings me to, and I don't want to talk too much about this slide except to make one point. That is all the work that the climate community talks about, really the climate systems are very chaotic, very difficult and very complex. And we've seen some of the illustrations from the talks earlier today, how complex they can be in the scale. But there's one benefit that hydrology community has is really the role of initial hydrological conditions. So it does take a fair bit of time for at least systems with larger storage to filter through that. So at least part of the predictability in the next sort of 3 to 5 to 7 days to a week, or even sometime to a month, can come depending on the hydrogeomorphic characteristics of the catchments that we're dealing with in various parts of the world. A lot of skills from there could be leveraged as well. So I think the climate predictions adds to the additional skill that comes from hydrologic skills, and there's work done in various parts of the world. How much of predictability comes from the initial hydrological conditions versus the climate predictability. What I'm going to go to next is a systematic study that we did as part of the Hydro S2S initiative. There are 30 catchments in various sort of tropical areas, mid-latitude, and also sort of mild and temperate areas in the south, and compared those catchment scale forecasts and catchment scale simulations and catchment scale observations from global models and the local models. So the global model, and there's a paper that's going out to HASTE basically this month, next month actually, and that quantifies some of those challenges that we saw. So these catchments, what I show here is the months on the horizontal axis, and each of these dot is a dot that corresponds to these areas here. So there are about 30 odd catchments, and you can see this is the forcing the global model with the reanalysis data set to bring in the hydrology at a catchment which can be somewhere in the 1,000 square kilometer to 5,000 square kilometer scale. When you do that, the biases that you get, the biases basically, both the negative and the positive biases are shown here, and you can see quite clearly that the reanalysis data sets from global models at the hydrologic scale is seriously biased, and therefore there is something that we need to think about when we think of reanalysis products and how we actually measure the efficacy of those products for hydrological application. And that has a flow-on effect. So one of the things that we all found from that was there are large biases, and generally underestimation in wet seasons and overestimation in dry seasons, which could be a systematic one, but in some cases there were unsystematic biases as well. And then you start questioning when you verify the global models with reanalysis data sets, and the local scale models are actually verified with observations. So there's a distinction that we need to bear in mind. And the next thing we show is obviously the water industry is risk averse. It needs that reliable predictions. And what we are showing here really is the 1 month forecast coming from a local model and from a global model. It's not important to focus on the model, which models here. The key message is very similar when you look at the different models across the two scales. The first thing you clearly say is the local models, they are generally far more reliable than the global models. The other thing this paper finds out is that the global models tend to give sharper forecasts than the local models. And that's not very uncommon because they're too emphatic and often too wrong. The third thing is the accuracy, and the accuracy that we expressed in the quantified CRPS, we find very similar things, that the accuracy is largely much skewed to the local models than the global models. So I want to come to some of the things that have been done in the services development. And these services were developed over the last 10 years. Fair bit of money has gone into this, and a whole lot of products that have been developed. What we figured out from that experience is, firstly, the operational agency and the research agencies had to really glue together into a formal governance arrangements where we could transfer the technologies from research agencies to operational agencies. And then the agencies also had to work with the water operators on how they want different products. I'm not going to go through these products, but each of those products have been developed after hundreds of consultations across the industry, across the country. And one thing that stands out was that you need products more in a way that agencies can use them. So it's not just enough to give the numbers, give the graphics, give the context, and then the second thing is the verification. And those verifications may not be always very scientifically conditioned. The science can sit behind, but you can basically color code. Green is good, purple is bad, traffic light type of concept to be used. So that's a 7-day forecast that's available in Australia every day now through an automated system. Similarly, there's a seasonal system that's underway. It gives basically to granular products at the sort of a local level, what's next 30 days, what's next 60 days, what's 90 days going to look like. How does it look like at a particular site, as an example? How does it look like across the country as a whole? What is the skill of a sort of this particular site across various months? In the hindcast, how does the forecast go over the last 12 months? So there's a lot of work done underneath for this. I can see I'm rushing now to few pain points. So I guess one of the drivers that I moved from the Bureau of Meteorology to a water operator agency is because to influence decision making, you really get to be inside the tent. And these are some of the priorities that I say coming from the water operators. There are flood operations that we need. We need to manage airspace and dams. We need to deliver water to various parts of the valleys, and there is a need for demand forecasting out to a season to a year. There's a need to account for inflows to dams, and many of these dams are highly regulated. There's a question around water security planning and the climate change impact. So there are some of the needs that we need to support through various applications. Not everything can be done through sub-seasonal to seasonal scale, but there's a lot of this area demands actually is on sub-seasonal to seasonal scale forecasting. The next point I want to make is, how does the concept really work? What matters? Why is it that we need forecasts? So the first thing is the agencies, there has got to be a system of rules. And in the valley, people have got access licenses. There are water sharing plans on how the water is to be shared amongst various users, be it consumptive users, be it environment. And then each shareholder of the water has got to have some say in the accounting. And the accounting is managed basically through a regulator who manages who has got what much license to share the water, and how much that person is taking or is allowed to take. The next thing we need is the storage. How much of water we have in our infrastructure that we can use to carry through the water year, for example. What are the impounding structure? What is the near real-time storage in this? The next thing is water availability changes based on droughts and wet cycles, or dry and wet cycles. So there are categories. There are high security water categories, low security water categories. There are human consumption, there's stock and domestic. There are a whole lot of things that you need to think, and all of those accounting rules need to account for each of those categories in a very structured way. The next bit is in Australia, the water rights basically and land rights are separate. So you can order, you can sell water temporarily or permanently. This is something like $4 to $5 billion trade annually. And the availability of water dictates the price. It could go from anywhere around, let's say, $100 a thousand cubic meter to something of the order of about $3,000 a thousand cubic meter. So that's the range, and it basically that trade can be quite a lot, and therefore we need to pay attention. So the next thing is the orders. So every day the river operator gets the orders. Every account holder orders, I'm going to need water for such and such time, and I need access to that water. And those orders are aggregated, and they go down up to the storage level. And the last thing that the aggregator needs to, the operator needs to know is what is the aggregated demand across the valley. Then comes how much water I've got available. I need to know what is the forecast, both of the inflow to the dams and the tributaries that are downstream of the dam. So that's why that 0 to 30 days and 0 to 90 days is important. Many of these valleys will have up to 6 to 8 weeks of travel time, and you need to know how much water you need to release, accounting for the transmission losses. So all of this requires forecasting at the subseasonal to seasonal time scale, which is absolutely critical. The other point I want to make, and I'll end very quickly, David, just give me a moment here. So this is, for example, a very important storage in one part of Australia. What it's showing is this time scale, if you look at carefully, roughly about 4 years. Every 4 years, we are seeing the sort of wetting, drying cycle. So what the operator needs to do is managing the infrastructure safety and the people safety, also ensure when you get high flows, you basically get your storage back to a level which is almost full across all the impounding that you can do in your valley, assuming today is the start of a multi-year drought. And that's really, really critical. And then we can support all of those needs that with the whole lot of rules and principles. So you can say it's a very complex business, and there are pain points. First, there are many, many forecast products that you look at in which parts of the GDPFS centers are there. There's very little guidance which forecast product we should use. Who is going to look after dealing with the biases that are illustrated around that? How do water sector gets access to the NWP data? And these are the questions that we're putting up as hydrology community to the climate community through Infrastructure Commission and the Services Commission. And I want to end with this sort of this thing that there's clarity needed on what forecast products to be used, not just clarity on what to use, but also rationale, whether it is fit for purpose. Access to NWP data is an important issue. The National Meteorology and Hydrology Agencies, in the case of India, for instance, IMD and CWC, need to work hand in glove with IITM and CMRWF and NIH. So that enterprise approach around working with the users, what needs are, understanding that there's a role, there's a need for global models because high resolution models cannot be everywhere, and there's a need for catchment models. Verification, we often talk of verification, but we mean very different things. So verification is important really to enhance end user confidence. And for that, it's not always the scientific metrics that matter. It's always to getting the users inside the tent through intuitive products. And the other point I want to make is the production of services are important. There are works underway in the hydrology domain. Different regions of WMO are at different levels of advancement. But there's, I think, one thing that we should not forget. Water operators have contingent liabilities. We cannot release water unless we basically either disturb the chemistry of the water sharing between users, or alternatively have unwarranted flooding. So those tension points means the use of this probabilistic information need to be in such a way that we actually have compelling reasons to take decisions which are optimal. Forecasts will always be imperfect, but how to make use of imperfect forecasts, in the words of Kurupa Kumar Kohli, to basically make optimal decision making. And I'll stop here. Thank you, David.
This is fantastic. Thank you. So we've reached the end of our allotted time. I hope that the administrators can keep the chat open for a few more minutes so that there can be some conversation about the latest talk. Otherwise, I think we've come to a close. I want to thank all of the distinguished speakers today and for all the participation from the rest of you. Thank you.
Thank you very much.
Thank you.
So you do have some questions there in the chat.
Yeah,
coming up.
no, only comment there from Dr. Peter to Narendra. So very nice. There is no question as such. So thank you very much to chair and all our speakers for maintaining the time. So I must thank Dr. Paul for, yes, we have maintained time, and also very excellent for talk. Thank you very much, sir. Yeah. And we'll be back in 5 minutes from now for the parallel session.
Thank you.
Thank you. Thank you. Yes, sir. Huh? Yeah. Now we are just opening hall B. Okay. You just I'm sending now again. Use go to hall B. Okay. Just I am sending. आनंद अभी तुम खुल गया ना? हाँ ठीक है, मैं राजगोपाल सबको कनेक्ट करेंगे, पूछे थे तो मैं लिंक भेजा उनको. अच्छा सर, अभी जो I have sent it ना, one PDF file there, PDF. You open that PDF file and there is a hall B hyperlink there. You just click it, it will connect. Just hall B, just see. Attachment. PDF open. Is there two files are there? No, one is PDF, sir. Just see. The doc might not be linked. Doc also link. Okay, B, yeah, fine.
Okay, I mean,
Yeah, yes.
I mean,
But you connected to hall A or hall B?
will be. Hello, hello, RFT man on paper and she say paper size. Yeah.
Okay, sir. So, Dimri sir, are you there?
Yeah, good morning, Dr. Patnaik. Yes.
Yeah, good morning to
Yes.
all of you. So now we'll be starting the parallel session in Hall A. Today is 23rd day of our workshop. So we have very distinguished scientist, Professor A.P. Dimri, Jawaharlal Nehru University. And as you know, I just like to introduce, very brief introduce. So he had a lot of work on Western disturbances, winter monsoon, and got various awards and recognition. So without wasting much time, now I will request Professor A.P. Dimri to kindly coordinate the session. Thank you. Over to you, sir.
Yeah, thank you, Dr. Patnaik, for kind words. Good morning to all of you. We are here in the parallel session of modeling monsoon processes. Monsoon is very key for us, and hence its modeling and understanding the process and dynamics in the changing time. So we have very important 6 talks in this session schedule. And as stated, we have roughly 13 minutes slotted to each time. And without wasting much time and to keep session in time, I request Dr. Manas Ranjan Mohanty, who will be speaking on seasonal prediction of ISMR using WRF, a dynamical downscaling perspective. Dr. Mohanty, are you here? Dr. Manas Ranjan Mohanty? Is not here. So can we move on to the next talk, Dr. Patnaik? Is it okay?
Go to the next talk. If he comes, then we will see.
Yeah. So Dr. Ankur Srivastava is here. Oh, Manas Ranjan Mohanty is here. Ankur Srivastava. Okay. So I could see
Ankur.
Srivastava. So morning, Ankur Srivastava. I request you to deliver your talk on interaction of rivers with the Indian summer monsoon, modeling impact on variability and implication for predictability. 13 minutes time. And I request Maheshwar Pradhan, who is next, to be ready after this.
Yes,
Dr. Ankur Srivastava, please go ahead.
Yeah. Thank you, Professor Dimri. I will just share my screen. Can you see my screen?
Yes, absolutely, I can see.
Great. So, hello everybody. I'm Ankur Srivastava from the Indian Institute of Tropical Meteorology. I'll be talking today about the interaction of rivers with the Indian summer monsoon. It's modeling the impact on variability and implications for seasonal predictability. It is known from various studies that surface runoff is an important component of the global hydrological cycle. Studies have shown that the interaction of rivers with the monsoon system modulates the enso-monsoon teleconnections, global SSTs and salinity, and is associated with an increased frequency of La Nina events. Further, especially in the Bay of Bengal, which is a highly stratified basin, the changes in salinity is linked to the rainfall over the Ganga and Brahmaputra river catchment area, which affects the mixed layer depth and the barrier layer thickness in this in the Bay of Bengal. Now, studies have also shown that barrier layers of the coast of Kerala caused by the freshwater transport causes SST warming and can cause an early monsoon onset. We know that Bay of Bengal is convectively active, which that means the fresh water, which causes the high stratification, facilitates the genesis of monsoon low pressure systems and hence can affect the convective activity on intra-season timescales. Therefore, since rivers are an important component of the monsoon system and they interact with the models should have a realistic representation of rivers. Now, if we see the climate forecast system version 2, which is used for operational forecasts in India, it has a prescribed annual mean climatological runoff into the ocean. Now, prescribing runoff is not a good strategy, especially for coupled models such as the CFS-V2. So we thought of replacing this prescribed annual runoff with a interactive runoff. So basically, how do you do that? How do we represent the horizontal transport of fresh water in our models? Basically, we take a digital elevation map, which is nothing but the topography. Based on this, we delineate the river basins globally and develop a flow network based on this DEM and pass the runoff generated by the land surface model through this flow network to get routed stream flow at land ocean boundaries. So we basically did two experiments with our model. First was the control run, which has the prescribed climatological discharge, and the RIV run has a routing model coupled to the CFS-V2. This shows the coupling strategy wherein the early runoff fluxes from the land model are passed through the routing model, which gives the early routed runoff at the land ocean boundaries and is passed onto the ocean model on every day. So basically, we did a seasonal hindcast for 1981 to 2017 with 10 ensemble members using February initial conditions. Okay. So basically, we wanted to study the three modes of variability, which is at the synoptic time scales, the intra-seasonal time scales, and the seasonal mean monsoon, which are basically important for the time scales we are interested in. So first we look at the monsoon low pressure systems, which are most important rain bearing systems for the Indian summer monsoon. The upper panel shows the track density of these systems in observations, the control run and the RIV run. And this shows the difference RIV minus CTL track density. So we can see that upon the inclusion of a routing model, the track density is higher in the northern Bay of Bengal and the adjoining land areas, and the associated. And this is the RIV minus CTL rainfall composite, which shows that the rainfall activity is also significantly higher by up to 1 to 1.5 millimeters per day, which means that they're enhanced due to inclusion of rivers. There is enhanced LPS activity in the model and associated rainfall also. Now, studies have shown that that the peak convective activity in the Bay of Bengal peaks at 28.6 degrees Celsius. This is the same number of LPS events grouped by the SST values, and we can see in the RIV model setup we get the peak of convection at 28.6 degrees Celsius in agreement with observations. The bottom panel shows the lifetime of LPS in days. So we can also see that the LPS lifetime has increased in the RIV. So to investigate what causes these changes in the low pressure systems, we did a mixed layer heat budget wherein this plot shows the RIV minus CTL mixed layer temperature tendency. So we can at different lags, that is from lag minus 5 days to lag plus 5 days. So we note that there is significant temperature gradients in the mixed layer heat budget, in the mixed layer temperature tendency, which is crucial for LPS simulation and enhances the moisture availability to the system. Then moving on to the intra-seasonal aspects, we looked at the monsoon ISO events, which are also important in modulating the rainfall activity during summer monsoon. And for those ISO events that occur under shallow mixed layer and thick barrier layer conditions, we did a lag composite -30 to +30 days of the mixed layer depth, barrier layer thickness, SST and rainfall. So we see post lag 0 represents the peak of convection. We observe that post the peak convection, the mixed layers are shallower and the barrier layers are thicker in the arrival run, which is the blue curve here. Now, due to this, due to the shoaling of mixed layers post convection and formation of thicker barrier layers, this causes an intense post convection break, and the ISO amplitude is also higher. So what causes these changes to the intra-seasonal aspect? We did a ISO centered composite, which we identified the ISO events, and 0 basically means the center of the convection, and north of it and to the south of it, this is the specific humidity, the vertical velocity, vorticity, and divergence. So we can see in the upper panel is the control run, bottom panel is the arrival run. So we can see the specific humidity is always higher to the north of the convection center for every meso event, which is basically responsible for causing the northward propagation of the mesos. And we can see that the specific humidity to the north of convection center is higher in the arrival run as compared to the control run. The vertical velocity is also higher. The associated vorticity to the north of the convection center is higher, and there is stronger lower level convergence and upper level divergence. So basically, this the improved upper ocean variability leads to enhanced GRC interaction in the bay. The stronger vorticity and specific humidity ahead of the convection center associated with the mesos should result in a stronger northward propagating pulse. So we check whether that is true. We plotted coherent, about 100 coherently propagating meso events. These are from observations. This is the control run and the arrival run. So we see the northward propagating pulse is the convection is stronger for this as compared to control run and much better organized. The SSTs associated with the monsoon active break phases is also better organized as compared to the CTL control run. Then moving on to the seasonal aspects, that is the interannual variability. We did a RIV minus CTL difference in the interannual mixed layer heat budget terms. The top panel is the temperature tendency and the bottom is the surface heat flux forcing. So we see there is significantly greater temperature tendency during June and July months, especially around the discharge locations of Ganga, Brahmaputra and Irrawaddy. And it propagates southwards as we move towards August, and this is basically caused by the surface heat flux forcing. The lag correlation between discharge and rainfall shows significantly positive correlations from -2 months to 0 months, and also at lead +1. These lead lag correlations between discharge and rainfall is somewhat stronger in the control run and is stronger up to +2 months. So this rainfall and discharge coupled feedback cannot be captured by the control run, which is well simulated in the arrival run, though somewhat stronger. Then we basically studied the implications for predictability. These are the anomaly correlation coefficients between observations and model. We see these are the skills for ISMR. We see significantly higher skills in control run, in river run compared to the control run. So just to summarize the mechanism, the fresh water from rivers causes an improved upper ocean stratification, which on the LPS front, it causes enhanced gradients in the Bay of Bengal due to the stronger asymmetric heat flux forcings, which causes frequent and longer-lived monsoon low-pressure systems. And at the intraseasonal timescales, the post-convection shoaling of mixed layers and thicker barrier layers form, which due to the changes in the mixed layer heat budget, which causes enhanced GRC interactions restricted to the shallow mixed layer and enhanced specific humidity and vorticity north of the convection center. which causes a stronger meso-associated circulation, which feedbacks to the monsoon low pressure systems, and both of these support each other to give a better LPS propagation and better representation of convection and synoptic intra-season timescales, and the scale interactions between them cause a better simulation of the season mean monsoon. Thank you.
Thank you, Dr. Nikur. Very interesting study linking with river to summer monsoon and like that. Anybody has any question, please, from the room, from the hall? I don't see any raised hands or something like that. If no one has, Ankur, I have many queries though understanding for my own self.
Yes.
When you are talking of Ganges and Brahmaputra, right?
Right.
That river is merging to Bay of Bengal.
Right.
And then you are also taking Irrawaddy, right?
Yes. Yes.
And the source of both the rivers are different. Am I right?
Yeah. True.
Source. So are you delineating the water source types, if I understand it that way, to
No,
the monsoon?
No, we are not delineating the water sources. Basically, the runoff is being generated by the land model. So we basically just delineate the river basin, and whatever runoff is generated by the land model in that river basin. Basically, the land model takes care of the sources of runoff, and my routing model just routes the runoff which is available from that basin.
Okay. Yeah, interesting. So my second question, if we have some kind of a isotope process analysis for this type of river water which is discharged in this Bay of Bengal, as we see, there are two different. So will there be any kind of differentiation coming into the oxygen isotope in this kind of? Okay, interesting.
Yeah, this is a very simplistic model. Basically, we are looking at the coarser scale, since we are only interested in the seasonal prediction, and we are only interested in whether the annual runoff is being simulated reasonably by our model. Perhaps the isotope analysis, which you might be talking about, requires a much higher resolution analysis, and we need to have traces in the model, and a much more complicated routing model which can account for the river basin scale topography also.
Yeah, thank you, Uncle. It's a very interesting and a very new dimension linking to the river. And this, thank you. I congratulate
Thank you,
for this
Professor.
work. And now we move on to the next talk by Dr. Maheshwar Pradhan. Improvements in the tropical diurnal cycle by incorporating forward flux algorithm in CFE2. Maheshwar Pradhan, Dr. Pradhan.
Yes, sir. I will just sharing my presentation.
Please go ahead and request to keep it for next 13 minutes roughly.
Yeah, sure. So hope I'm audible and my presentation is visible.
Yes, you are audible and your slides are seen. Thank you.
Yes. So, hello everyone. Good morning. I am Maheshwar Pradhan. I'm working at the Indian Institute of Tropical Meteorology, Pune, and simultaneously I'm doing my PhD from IIT Bombay. And in next few slides, I'll be presenting how the coupled model simulation can simulate tropical diurnal cycles in a better way, and by incorporating the turbulent flux algorithm and diurnal temperature schemes. So I'll be focusing on two diurnal temperature variability. So one is called Coolskin temperature, which is basically formed whenever there is a net radiative heat loss from the ocean and atmosphere interface, and that is due to the net radiative loss by long wave sensible heat and latent heat. And at that point, the interfacial layer is relatively cooler than the bulk ocean temperature, and this happens mostly during night times. And second one is the warmlet temperature, which forms because of the net radiative heat gain by the interfacial layer. In this condition, the skin temperature is warmer relative to the bulk ocean temperature, and various components. That is mainly due to the net radiative balance between short wave and heat losses due to long wave and sensibility and latent heat fluxes. And both of these diurnal temperature variations are much more sensitive to wind conditions and the cloud or convection condition over the oceanic part. So various studies have reported the importance of diurnal SSTs over on the surface as well as subsurface ocean at a longer time scale, such as synoptic to interseasonal time scales, as well as many studies have reported their impact on the atmospheric properties, such as Wellinger et al. 2010 have reported the diurnal convection characteristics is significantly modulated by diurnal SSTs. Then over the ocean, the amplitude of synoptic to interseasonal SST variations are either and can be amplified or can be subdued by process called rectification, which is reported by Muzumdar et al. 2011, Yan et al. 2021. And the possibility of enhanced equatorial upwelling because of this modulation of equatorial current by diurnal SSTs are also reported by some of the sensitive model experiments carried out by Bernie et al. And the interseasonal to seasonal timescale mixed layer processes are also affected and are reported by Shinoda et al. And others. At longer time scale, the ENSO-related nonlinearities like SST skewness and various ocean atmospheric feedbacks are also altered by these diurnal SST variations and are reported by Mason et al. Just to note that 1 Kelvin error in the SST skin temperature can lead to around 30 watts per meter square net surface heat fluxes, and this can lead to from modeling perspective, it can lead to spurious signals in the coupled models. So next, to incorporate the diurnal variations in our coupled model, so we carried out two sensitivity experiments. One is called control run and another is sensitivity run. In control run, we basically take the default anchor flux scheme, and in sensitivity run, we have implemented the coerced flux scheme. And the difference of coerced control and sensitivity run basically depict the difference between anchor flux scheme and coerced flux scheme, and is tabulated here. The basic difference is that coerced flux scheme takes care of the warmlet temperature corrections and cool skin temperature corrections. Along with that, the parametrization of stability functions, gustiness, and roughness lengths also differs in these two algorithms. And we have carried out the hindcast for a period of 1981 to 2007, and we are focusing on during the monsoon season, that is JJS. So to first to see the implications of implementing diurnal SSTs in the model, we have taken few buoy locations as observation, and we have validated our model results against these buoy locations. And here I have plotted the SSTs in the observation as well as two sensitivity runs. And these are plotted against local solar time. So in observation, which is represented in blue color, the dashed line is the control run and the dotted line is the sensitivity run. What we can see that in control run, both the diurnal maxima and diurnal minima are shifted are shifted and delayed in nature as compared to the observation. But in sensitivity run, that is quietly improved. And this is a location for Bay of Bengal. And here, both the timings of maxima and minima are quite improved. Similar inferences we can find from locations like these two locations are over Pacific. And in these two locations also, timings of maxima and minima are quite improved in the sensitivity run by implementing diurnal temperature schemes. And another thing you can infer from this plot is that the range, the maxima to minima range in the control run is quite less as compared to the sensitivity run and as also compared to the observations. Those, to validate the diagonal range again, we plotted here like global plot by taking observations and control run, and we defined seasonal diagonal range DSST as maximum minus minimum in a 24-hour cycle. And for the period, this is for observation is restricted to that period. That's why we restricted our models, model results also in this duration. So what we can see that in the observation, the diagonal range is ranges from 0.4 to 0.7 degrees centigrade over the tropics and northern hemisphere. This is basically the summer hemisphere. In the control run, the diagonal range of SST is quite restricted up to 0.2 degrees centigrade, 0.2 or 0.23 degrees centigrade. But by incorporating diagonal temperature schemes, we have seen that the sensitivity run quite well represent the diagonal range of temperature, and the enhancement is around 0.2 to 0.3 degrees, 0.4 degrees centigrade, and it well represented the diagonal range of SSTs. So to again similar to the SSTs, we saw the implications in the subsurface by taking by computing the MLDs from the buoy observation as well as from model simulations. And the blue line again shows the observation, and the dashed line shows the control bar. Here also we can see that the mixed layer variation, that shallowing of mixed layer during the late afternoon, and the deepening of mixed layer in the early night is the difference is used in the observation, and the model sensitivity run also it reproduces the range of MLD quite well. But in control run without having the diagonal schemes, the range of MLD is quite not significant as compared to the sensitivity run or the observation. Specifically, the nighttime deepening of the MLD is not well reproduced in the control run. Sorry. So similarly, we define diagonal range of MLD as maximum minus minimum MLD during the 24-hour cycle, because the observations were not available, high frequency observations were not available. We restricted our analysis to model simulations also. And if you can see the difference plot of diagonal ranges, the whole tropical ocean has enhancement of diagonal range of MLDs by up to 10 to 15 meters in the tropical oceans. So to link the diagonal SSTs, how they impact the atmospheric conditions, we have taken this plot from Bellinger et al. 2010, where they have reported how the atmosphere behaves with in presence of warm layer DWLM, diagonal warm layer, strong diagonal in presence of the strong diagonal warm layers, and in absence of diagonal warm layers. What they have reported, just to summarize, I am not going into the details of this plot. What they have suggested that in presence of strong diagonal warm layers, the wind condition, horizontal wind conditions are calm, and there is a reduced downdraft and increased mixed layer height of the atmosphere, and the precipitation is reduced in these conditions. And it is also accompanied by reduced latent heat flux or sensible heat flux. To carry out similar analysis in our model simulations, we have also done composite analysis for warm layer events, where warm layer events we defined as where dT1 is greater than 1 Kelvin temperature. And the left panel shows the horizontal wind speed. The middle panel is for precipitation, and the rightmost panel is for latent heat fluxes. But we can see that whenever diagonal warming is higher, the control run simulates higher wind speed, whereas it is supposed to be calm wind conditions, and it is well reproduced in the sensitivity run by implementing the diagonal flux and temperature schemes. Similarly, the precipitation is overestimated is a control run over the equatorial belt of Pacific and Bay of Bengal, Eastern Indian Ocean. But this was not supposed to be there because Pellinger et al. Suggested that it has to be accompanied with reduced rainfall. And similarly, the sensitivity run well reproduces these conditions. Also, Bellinger et al. Suggested that the warm layer events has to is accompanied by lower latent fluxes, which is not reproduced in the control run, but it is quite improved in the sensitivity runs. So how the diagonal schemes can impact the precipitation events in the diagonal range is represented here. The first plot is from observation. We can see that the diagonal range is quite significant over Bay of Bengal and Eastern Indian landmass, Western Ghats, and Eastern Indian Ocean, and the equatorial belt of Pacific and Atlantic Ocean. So if you see the control run, the diagonal range of precipitation is hugely underestimated, and that is significantly improved and quite in agreement with the observation in the sensitivity run. And the mechanisms of how diagonal range, diagonal SSTs can impact the diagonal precipitation are reported in various studies, and not going into the details. So basically, just to summarize, diagonal SSTs can improve the diagonal range of precipitation. Further, to see how if the diagonal phase of precipitation can be improved. Yes, sir.
Dr. Pradhan, sorry for interrupting you. Can you wrap it up, please?
Yes, last slide only. So diagonal phase of precipitation. Many studies have reported that there is a well-marked signal from Indian landmass to Bay of Bengal in the diagonal phase local cycle, and that is well reproduced in both of the model simulation. And we have not changed any parametration related to land sea breeze or overland parametration also we have not changed. That's why we are not expecting any huge improvement in the phase propagation of precipitation. However, the Western Indian landmass there is some improvement of the phase propagations also. So to see how the diagonal SSTs can improve can further go into the seasonal and subseasonal scale. I encourage all you to refer to that paper I have shown in the third slide. So that will be all from my side. Thank you. Yes. Hello. It's not audible, sir. You're muted.
It's a good effort of tweaking or correcting the cool skin and warm layer SST temperature. There is a time for one quick question if somebody has a question to Dr. Pradhan.
Yes, sure.
Do you have any question, anybody? Okay, if nobody has, we have quickly moved to next presentation by Dr. Anumeha Dubey. I hope Anumeha is here. Spatial verification of probabilistic rainfall forecast over Indian region. Dr. Anumeha, please go ahead. Yeah, thank you.
Sir, I hope my slides are visible.
Yes, I can hear you. I can see the slides also. Thank you.
So good morning, everyone. The topic of my presentation today is the spatial verification of ensemble rainfall forecast over the Indian land region. So why do we need to go for the spatial verification is that because of the increase in the computational power, we have very high resolution NWT models, but when we try to verify them with the available observations, more often they suffer from a problem of double penalty, which is due to the location mismatch between the observed events and the forecast events. And this results in very poor scores if we go in for a grid-to-grid verification. And therefore, the actual advantages of a high resolution model can never be fully realized due to this problem. The advantage of spatial verification is that it does not require a grid-to-grid matching between the forecast and the observation. Instead, it does a match between a forecast object and an observed object. So there are many methods that are available for the spatial verification. The one that we have applied is the contiguous rainfall area, the CRA method. In this, there are objects both in forecast and observations which are defined by a particular rainfall threshold. So whatever area is enclosed within a contour of a particular rainfall amount, maybe 10 millimeters, or if you want to go for higher rainfall, maybe like 40 or 80 millimeters per day rainfall. And then we try to compare these two objects and the different components that are described by these objects, like the maxima that is present between these, or the amount of rainfall in terms of the volume, the area, or the rain rate as well. So these can be compared, and these can be used to quantify the biases. Also, the total error in this case can be defined as a contribution from displacement, volume, and pattern. Now, there are many studies that are available for the verification of deterministic forecasts, but for ensemble forecasts or probabilistic forecasts, not a lot of work has been done. So this is our effort in that direction. We have chosen 3 monsoon seasons from 2018 to 2020 over Indian region using the model LCMRWF ensemble prediction system, which has a horizontal resolution of 12 kilometers, and it's a lagged ensemble system with 23 members, 1 control and 22 perturbed members. So our main aim is to see what is the maximum contribution coming from, whether it's displacement, volume, or pattern. And also, we usually do a spread scale comparison in order to see if the ensemble system is well formed or a robust ensemble system. And that is what we have tried to see in case of the object parameters like maxima, volume, or area. And then we have done a probabilistic verification of these object parameters. So in this case, we have chosen 3 regions. The big box in the center is the core monsoon region, which gets a lot of rainfall during the monsoon. And then we have the west coast. For this, we have divided it into 2 parts. The northern part of the west coast, which covers the area of Maharashtra and Konkan region. And then we have the second box, which is mostly over Karnataka and Kerala coastal regions. So this is a result for a case of 2nd July 2019, where there was a heavy rainfall over Odisha. So the top panel on the left here shows the day 1 forecast from the deterministic NCMRWF model, NCUM-G. And the bottom panel here is from the observations. So if we look at it, we see that the observed pattern is slightly different from what is being forecasted, as well as the location of the maxima is different. So these are the kind of results that we get. First of all, it gives how much is the displacement between the forecast and the observation. So in this particular case, it is 2.5 degrees in the eastern side and a 1/4 degree in the northward direction. Then it also tells about what is the difference between the rain rate in the 2 entities, then the maxima, rain volume, and what are the contribution coming from to the total mean squared error. So in this case, we see that the volume is pretty well predicted, but the major error is coming from the pattern. Now, this is one case, and if you look at the same case for the ensemble prediction system, we see that there are 23 members. In the bottom right panel here is the observations. So we see that all the ensemble members are predicting the rainfall, but it is very evident that the maxima here is predicted at very different locations, and all of them have very different structures as well. So this is the blue patches here are the rainfall exceeding 4 centimeters per day, and from the observations also we see. So this makes it very clear that all the ensemble members are predicting it at very different locations. Okay, so the first thing that we actually analyzed here is how the members are displaced with respect to the observations. So this is the top 2 panels are for the west coast, and they are mostly the displacement was seen in the northwest southeast direction, probably because of the orography. And the displacement in this case is confined to plus minus 3 degrees in the east-west direction. The last row here is for the core monsoon region, and the displacement is more in the east-west direction, and it is also higher than what we see in the west coast region. It is spreading up to plus 6 degrees on the eastern side. Another interesting thing to be noticed here is that with the increase in the rainfall thresholds, that is for 40 and 80 millimeters, the displacement of the members is actually lower, or the systems are more organized in that case. If we look at the total mean squared error, then as expected, the error is increasing with the lead time. And also it is higher for higher thresholds, but the least error is seen in the core monsoon region. If we look at the individual contribution from the different components, displacement, volume, and pattern, we can see that pattern contributes the maximum. So the pattern error, this is usually true for almost all the cases where pattern contributes the maximum, and usually the volume of rainfall is quite well predicted in all the cases. And once again, in the core monsoon region, the contribution from displacement and volume is low, but for the pattern, it is the highest. So looking at the RMC versus the spread, we have chosen 3 parameters here, that is maximum, volume, and area. We see with the increase in the rainfall threshold, which is, if we move column wise, there is a lot of difference between the RMC and the spread. For a good system, they should actually be aligned very close to each other. So it increases, that means the skill of the forecast is decreasing. But in case of rainfall volume and area, we see with the increasing threshold, the model is able to perform better, or there is more skill in the model. If we look at the probabilistic attributes, we see that once again, the volume and area are performing much better because they have a lower Brier score, which is a difference between the probability and the observations, forecast probability and the observations. So it should be as close as 0 as possible. So for both volume and area, it is much lower. The Brier skill score should be higher. It should be closer to 1, and it's not close to 1, but still for volume and area, it is higher. Whereas for maximum of rainfall, it is becoming negative also. Then if we look at the rock curve, we see that the volume is actually doing a better job, because this curve should be aligned along the top left diagonal for it to be a good skillful forecasting system, and which is followed by area, and finally maxima is very close to the diagonal line. Then we have the reliability curve here, which also shows that for rainfall maxima, for a good system, it should be aligned along the diagonal. So the forecast probability should be similar, should be the same as the observed frequency. And in this, the reliability curve for the maxima is further away from the diagonal line as compared to the volume as well as the area. And finally, we have the area under the ROC curve, which is just the area under this curve. And this should be 1 ideally for a good system. So we see that for volume and area, this is higher, whereas for the rainfall maxima, this is much lower. So in conclusion, what I wanted to say through this is that the intensity of rainfall is a challenging attribute to predict, whereas volume and area are better predicted by our ensemble prediction system, and therefore we are trying to develop more and more products which make use of these skillful attributes. And the intensity of rainfall is requires some kind of post-processing or bias correction methods for it to be more of for it to be more accurate. That's it from my side. Thank you.
Thank you, Dr. Dubey, for keeping in much time. There are time for questions. Is there any question for the talk on the talk, please? Anumeha, I just want to know two things in this continuous rainfall area. It's a basically statistically driven techniques, right?
Sir, it's not statistically driven. What we do is we take the 2 objects that are formed, within the forecast and the observations. Then the forecast is moved and shifted over the observations, and then it is rotated. So a best fit is obtained between the forecast and the observed object. And based on that, then we calculate how much was it shifted, how many points within the forecast are excluded when it is matched with the observations. So all of that gives you the error.
Yeah. So that's why my query was in fact, when you are talking of rainfall volume,
Yes, sir.
how you are looking for rainfall volume in this switch from one point to another point?
So, sir, when we translate the forecast over the observation, some points from the forecast can actually be removed. So there is a criteria that not more than 25% of the points from within the forecast objects can be excluded while the match is conducted. And then there are a number of grid points that are present within that forecast objects. And there is rainfall forecast available on each of those grid points. And that is used along, and the area obviously we know because of the object, and so that is used to calculate the volume.
Yeah, okay. Thank you very much. I congratulate for employing new technique, new methods. Thank you, Anumeha. Yeah.
Thank you, sir.
So we will move on to next talk by Dr. Ashish Kumar Mitra. Mitra, sir, are you here?
Good morning. I'm here.
Yeah, good morning, Professor Dr. Mitra. The talk is on implementation of a seamless modeling system at NCMRWF Ensemble Monsoon Prediction from Hours to Season. Dr. Mitra?
Yeah, I've shared it. So is it visible in full screen?
Yeah, I can see, not full screen. Maybe you have to do full screen. I can see.
Thank you. Yeah, now I've done it full screen. So I will be briefly presenting the seamless modeling system at NCMRWF. So it's one of the unique modeling system in the world. So why? 1 minute, the slides are not moving. Yeah. So this center is under the Ministry of Earth Science, and our main mandate is to underpin the forecasting capability of the National Weather Service. And we are also responsible for the data assimilation system, and we are also mandated to develop and implement the seamless modeling system and develop applications. So as we know, from various scale, there are applications of these weather and climate models. And the seamless modeling system, so it's a unique thing which caters from smaller scale to even climate change scale. So that's the beauty of this seamless modeling system. There are many advantages of this seamless modeling system. So I will go to the last but one point that it makes the synergy between short scale and climate scale. So if you see, many centers are still developing the seamless modeling system, but we have implemented it in collaboration with our partners. And because of the continuous increase in HPC and model resolution and data assimilation, the skill of the model is continuously improving. You can see how the RMS is decreasing over the years. And if we compare with other lead center, we are also very close to them. And that's mainly because, as I said, due to the data input. So huge amount of satellite data is being put into the model. And we also compare with ECMWF always this data. And this HPC, continuously we are improving our HPC. Now we have 2.8 petaflop of HPC, and we are targeting another 15 to 20 petaflop by this year. And we have many users, but our main user is IMD. And one example, there are customized forecasts also we give when agencies approach us. So you might have heard about the Indian Navy's Tarini team, all-women team, which circumnavigated the globe. So the weather and ocean forecast we are supplying from this center. And apart from that, we have many other users, government, and interestingly, many private companies, energy, wind energy and solar energy companies, they are coming forward. And this center also caters to the BIMSTEC association. So the BIMSTEC country also closely work with us. We train and share our products. And all this is possible because of the MOES collaboration with the IWM consortium. So we have core partners like Bureau of Meteorology, New Zealand Met Department, South Africa, US Air Force, Met Office. So this is all the development of the model and data assimilation system is possible because of this government to government collaboration under the UM consortium. So we have under the seamless modeling system, global and regional data assimilation, land surface data assimilation, and ocean data assimilation system. And these are the data, satellite and in situ observations which are used in the assimilation system. And we have another very interesting system developed here called the FSOI. So it shows the impact of observation. This is very useful when we work with ISRO and other agencies, that what exactly is the impact of a particular observing system in the forecast. So we can optimize the use of observation, and a lot of resources can be optimized by this way. And recently we have implemented something called ELUS Wind, and it has a very good positive impact in the model. And the IMD's radar. So our main priority is now to assimilate all the radar into the seamless modeling system for severe weather in shorter time scale. We are also developing something called HRR system. So that means every 1 hour you assimilate and forecast for next 9 to 10 hours. So this is also a priority. And the land surface assimilation we are already doing, but this is also a priority. Currently we are assimilating only satellite soil moisture, but we plan to incorporate other observations into this. And another important thing, there are separate talks that under the regional data assimilation, we have produced a very good data reanalysis 12 kilometers. So there are separate talk on this. So until now, what I saw, 18,000 users are registered for this product. So coming back to the seamless modeling system, so you can see very fine scale 330-meter Delhi model, 2 coupled global model for extended and seasonal prediction we have configured at various scales. So the same dynamical core is used across scales. So it's very beneficial. So these are the different models we have from part of the seamless modeling system, and the ensemble prediction system also is there. So as I said earlier, it caters from very small scale Delhi fog model to extended and seasonal prediction. The single dynamical core does this job. So these are some of the recent results, like the Kerala rain, and we saw the regional model is doing much better, and the Uttarakhand rain also signal was good, but the regional model captured it much better. And these are some of the scores for 2021 monsoon. We do it for each monsoon to improve the model. So there are biases in the model, but when we compare up to 5 days forecast and compare with other centers, as I showed, so they are at par with other centers. And this is another thing which you can see in the internet coordinated by ECMWF, that where our model stands compared to other models. So the website I have seen here, we do it very regularly. And another application that for the basin scale, for hydrological application, how good is this forecast? So we saw the regional model is much better compared to the global model because of the resolution. And this is the Delhi fog model. So we have compared with observation at Delhi airport. So the temperature, moisture, visibility agrees well. So this is used by IMD for winter fog prediction. And we are trying to improve this by improving chemistry and more urban morphology into putting into this. So this model will be replicated to other cities as an urban model. Coming to the ensemble prediction system, we have 2 ensemble prediction systems, regional and global. So this is one of the highest resolution model in the world, and this is shared with ECMWF. So all the data people interested can download from ECMWF, and it's very useful for defining the probability strike rate for the tropical cyclone. Similar thing for the rainfall also, we give probability of heavy rain, etc. So these are 2 examples of 2021 cyclones. So very good ensemble mean products prediction was there. And you can see the uncertainty from the ensemble prediction system, which is very useful for administrators. Similarly, for heavy rain also, this is the Kerala rain, it was showing that probability more than 11 centimeter. What is the probability? It was 75% probability what it was showing. Similarly, for the Uttarakhand rain, it was showing the probability that there is a high probability between 50, more than 75%. So these ensemble prediction systems are very useful. And recently we have developed this lightning forecast in terms of probability. This is a new product. You can see it in our website. Now coming to the coupled model part of the seamless prediction system, we do extended range prediction, which is very useful for predicting the dry wet spell. So how nicely 3 to 4 weeks in advance, the week and dry spells are captured. You can see here as a sample from 2021 monsoon. And the onset of monsoon also, we predicted 4 weeks in advance. There was a delayed monsoon in 2019. And seasonal prediction also has very good skill compared to any other model. So 2021, it was showing average to above average rainfall, which came out to be true. And we have compared with ECMWF forecast and compares very well with ECMWF forecast. And so for this initializing the coupled model, we have ocean data assimilation system. It's one of the best ocean data assimilation system, almost same as what ECMWF uses. And we have compared with our Rama buoy. They perform very well. And the tropical cyclone heat potential, which we share with IMD, is very, very useful in cyclone monitoring. Very recently, we have developed a 9-kilometer global model. So we are upgrading our coupled model, and we have tested the very high resolution AD resolving ocean model, which is 9 kilometer. So it will be implemented with the new HPC. And very recently, we are developing a regional coupled model also. So we have seen when you include the wave, fully coupled atmosphere, ocean, wave, and land surface with hydrology, the best prediction comes. It's a case study of cyclone. And so this will be in place as soon as the new HPC comes for severe weather and cyclone. And we also have the capability to predict for the polar region. So this is used by NCPOR whenever there is a requirement. So we have the capability to simulate the polar sea ice as part of this coupled model. Very useful for our MOES operations there. With that, I'll finish. So mainly we'll be working in future with the new enhanced HPC. We want to mainly go to the coupled NWP. So ECMWF is the only center which has gone to the coupled NWP. So we are working, we have already tested it, it's in place, but HPC is the bottleneck. So when we get the new HPC, we'll do medium range coupled NWP, and ensemble members will increase. And the last item is to enhance the users, how to use this ensemble prediction system for all applications. So thank you. With that, I will finish. Thank you very much.
Thank you, Dr. Mitra. There are a lot of advancement you have introduced in the present forum, and it's very appreciable that various climate phenomena as well as the modeling strategy, the center is advancing with time again and again. Any question probably for an overview shown by Dr. Mitra about NCMRWF? Okay. Out of very different contexts, Dr. Mitra, I just want to know why these kind of things can surely will be interacting with academic students, I believe, who do not have the HPCs to simulate, like JNU, like any other universities, maybe.
Yeah, definitely. Yeah, we'll be very happy to collaborate with academic institutes. We are having selected, but yeah, one of the recommendation is to work closely with academic institute. Yeah, we'll be happy provided the proposal lies with the mandate of the center. So we'll be very happy to work on that, particularly developing application. Yeah.
Yeah, thank you, Dr. Mitra. It's a very impressive introductory overview of the NCMRWF in various dimensions. Thank you.
Thank
so
you.
we move to the next. Dr. Sri Kala PP is Dr. Sri Kala PP is here.
Yes, sir, I am here.
Yeah, please. So we are having the next talk on the simulation of northeast monsoon rainfall over southern peninsular India in CME 5 model. Dr. Sri Kala PP, please go ahead. Can you go ahead, please?
Sir, just 1 minute. Is this visible?
Yeah, it's visible, but it's need to be done 90-degree east rotation, orientation. Can you hear me?
Yes, sir. Yes, sir.
Yeah, can you rotate it? or maybe I request organizers if they can pop her slides. Is there somebody from organizer team? I don't know.
Yes, we will share and we will control. You can
please. I'll request. I'm sorry. I'll request the administration.
Yes, sir. Just 1 minute. I'm sure.
Yeah, it's better now.
My topic is.
Can you be louder? Can you be louder, Dr. Srikala? You speak louder.
Okay, sir. Am I audible?
Yes, it's better now. Thank you.
Okay.
Please go ahead.
Okay, my topic is on the simulation of northeast monsoon rainfall over southern peninsular India in SIMI-5 models. Next slide. Yeah, coming to the introduction, as we know, it is the rainfall is more over the southern peninsular India, especially over Tamil Nadu region, where we don't get enough rainfall during southwest monsoon season. So it is important to study the variability of northeast monsoon rainfall over Tamil Nadu. Next. Okay, this is the seasonal rainfall. As you can see, the rainfall is more over the maritime continent, and on an average, 334 millimeter rainfall we are receiving over the southern peninsular India, and its CV coefficient of variation is very high, 25. It makes the prediction of the rainfall difficult. Next. So the motivation of my study is based on I have done some trend analysis for northeast monsoon rainfall from 1979 to 2012. We found that there is an increasing trend in northeast monsoon rainfall over ocean as well as over the land. So we would like to check what will be the future. So we wanted to first we wanted to check the skill of the SIMI-5 models. So I did the analysis of 35 models, how well the models are simulating the northeast monsoon rainfall. Next one. Yeah, I just already discussed. So we know the interannual variability of northeast monsoon rainfall is positively correlated with ENSO and IOD. It is opposite to the southwest monsoon rainfall. But we have seen a poor skill is in simulating the mean state and interannual variability of northeast monsoon rainfall. Actually, in the models we have seen the relationship between the northeast monsoon rainfall and El Nino is opposite to the observation. Next one. So here I'm showing the data set I used. There are 34 models, and other observed data set is from hard ISST and ERA5 wind data set and the GPCB rainfall. Next one. Okay, coming to the results, as you can see, there is a multimodal ensemble and observation. There is a positive rainfall anomaly over the southeast Indian Ocean, southwest Indian Ocean region, and in the Taylor diagram, we can see many models are predicting the correlation is between 0.6 to 0.9. And I have selected 5 low skill models and 5 high skill models, and I did a comparative study. Next one. So this is the bias in multimodal ensemble and high skill model and low skill model. This is for first one is for rainfall, and next is for wind. What we have seen is in LSM, that is in low skill model, the observed equatorial westerlies during this season is not simulated well, and there is a convergence of the southwest Indian Ocean region, and we can see a positive bias in the rainfall over that region. So since the model is not able to simulate the equatorial westerlies, I think this negative bias over peninsular India and positive bias over southwest Indian Ocean is observed in low skill models, but it is better in the high skill models. So did the bias in SST and wind. Here also we can see in HSM model, sorry, in LSM model, we could see a positive SST bias over the southwest Indian Ocean region and negative SST bias over the southeast Indian Ocean region, and it can be it is manifested in the Walker cell circulation as well. We could see a ascending motion over the this 40 to 60 east region, which is responsible for the positive bias in rainfall over southwest Indian Ocean region. Next is. So I did analysis on interannual variability. Next. So from the observation we have seen during El Nino, we could observe positive rainfall anomaly over Western Indian Ocean as well as the peninsular Indian region, and negative rainfall anomaly over the Eastern Indian Ocean. And just opposite kind of anomalies observed in La Nina composite. And IOD and El Nino composite of rainfall is similar, and while La Nina and negative IOD composite is similar, with negative rainfall anomaly over peninsular Indian region during La Nina and negative IOD. So we wanted to check whether the models are able to get this signal. Okay. Next. So this is the observation. Probability of excess during El Nino is 0.27, and for an ENSO IOD year it is around 0.63, and probability of normal and excess is 0.88 for an ENSO IOD year, and 0.75 for La Nina year, while 0.82 is for El Nino year. So this is the SST composite of flood. And we have seen the correlation of southern peninsular Indian rainfall with Nino 3.4 SST, and also with DMI. DMI is this orange color, and Nino 3.4 SST is blue color. So here, as we can see, most of the models, around 70% of the models were not able to get the observed positive correlation between the El Nino and northeast monsoon rainfall of southern peninsular India. So 70% of models were not able to get this relationship. So again, we have selected some low scale and high scale models on the basis of this correlation. Next. So this is the result. This is the regression map of Nino 3.4 SST onto the northeast monsoon rainfall and SST and wind. Here SST is the shaded portion and rainfall is the contour lines. So in the low scale models, we couldn't observe the positive rainfall anomaly over southern peninsular India. In the low scale model, we have also seen a extended cold tank SST. This warm SST over this cold tank is extended more westward. But in a high scale model, even though there are many error we could see, but the rainfall over southern peninsular India is better simulated in the high scale model, and SST over the Western Pacific is mostly similar to the observation. This is the observation. Next one. A similar kind of analysis is done for the dipole mode index. We could see a similar kind of result in this one also. Next one. So I did an analysis for the Hartley and Walker circulation. So we can see from the observation, we could see a ascending anomaly over 5 to 10 degree north region. This is actually related with the rainfall over this region, and this could find in a high scale model, but there are a serious error in the 10 south to equatorial region. This descending motion is not observed in the observation, but still high scale models are based on the southern peninsular Indian rainfall. So this ascending anomaly is observed in high scale model, but not in the low scale model, where we could find descending anomalies over this region. Next one. Okay, this is a similar analysis for the IOD. Here also we could, even though there are erroneous simulation for this descending anomaly, but we could see a ascending anomaly over the 5 to 10 degree north region. Next one. This is for the Walker circulation. Here also we could find in 60 to 80 degree, that is our region, we could find a ascending anomaly in the HSM as well as in the observation, but that is not observed in the LSM, and also this descending anomalies are more is extended more towards western region in the LSM model. That could be a reason for the negative rainfall anomaly over the southern peninsular India in the LSM models. Okay. Next one. Next. So coming to the conclusion, CIMIT-5 models capture the mean northeast monsoon rainfall over Indian Ocean and southern peninsular India reasonably well, with a pattern correlation ranging from 0.6 to 0.93 and RMSE between 1.73 to 3.83. So positive IOD like mean SST bias in Indian Ocean and weak La Nina like mean SST bias in Pacific Ocean is observed in the low scale models. And low scale models could not simulate the observed equatorial Indian Ocean westerlies, which leads to the abnormal ascending motion and unrealistic wet bias over the Western Indian Ocean and dry bias over the southern peninsular India, Southeast Asia and Southeast Indian Ocean. So around 70% of CIMIT-5 models were not able to capture the observed positive correlation that exists between the southern peninsular Indian rainfall and 3.4 SST as well as SPR of PMI. And El Nino and PAOD related warm SST anomaly over the equatorial Pacific cold tongue is found to be extended more westward in the low scale models. And along with the westward extension of the cold tongue, the observed El Nino and PAOD related anticyclonic circulation over the South China Sea and Bay of Bengal is found to be shifted more westward. This is manifested by the unrealistic westward shifting of descending anomalies up to 70 degree east in the Walker circulation. And this descending anomalies over the northwestern Indian Ocean and southern peninsular India causes erroneous dry anomalies over the southern peninsular India and negative correlation coefficient between southern peninsular Indian rainfall and 3.4 SST as well as southern peninsular Indian rainfall and dipole mode index in low scale. Thank you.
Thank you, Dr. Srikala, PP. Is there any question for the talk on Northeast monsoon? If not, thank you, Dr. Srikala. Right? Thank you for interesting talk. And if we have few minutes, if anybody has any comments, question, queries for a general house, I invite. If not, then I thank you all the speakers for their excellent presentation and advancement in the process of the monsoon modeling, monsoon at different scale, and their themes leading to the better prediction in the future modeling strategies, statistical strategies for a better prediction for extreme weathers. They are very important nowadays. Various techniques improvements are there, methods are improving, data is observations are improving. So I'm very happy to be part of that, and I specifically thank the organizer of International Workshop on Monsoon for giving me this opportunity to coordinate. With these words, I thank you all, and I hand over this to the administration. And thank you, administration, to handling this session well. Thank you very much. Thank you, Dr. Patnaik, as well. Over
Thank
to you.
you, Dr. Yeah, Professor Dime. Thank you very much. Actually, yes, very interesting talks were there. Yes, but starting from modeling aspect and seasonal forecast, then last talk from Cochin University. So variety of talks were there. I think it is very good. We actually we missed one talk in the initial thing. I think we could not get proper communication. Otherwise, we could have arranged it. But anyway, so it is very good session. And thank you, I think, all the speakers and chair for the very wonderful session. Thank you. And again, the hall B, it is going on 11:30. It will be over, and so we will be going for next session. That is the short oral session that will start at 11:45 local, that is 11:45 local time in hall A, that is about 6:15 UTC. Yeah, 6:56, 11:30. Yeah, so 6:15. So we'll come back at after about 25 minutes from now. Thank you very much, sir.
Dr. Busher. Dr. Busher.
Sir, yes, sir.
Yeah.
So please 1 minute.
Yes, you gave me a green signal so that we can start.
So thank you very much for our first short oral session, and we have 18 talks. So now I request Dr. S.I. Laskar, the scientist E, and also the IMS Joint Secretary to kindly coordinate this session. So since we have 1 hour 45 minutes for the entire 18 talks, and we can have slight flexibility. Earlier we were thinking it is 2.5 minutes. It can be slightly higher. And if the person finish in time, you can allow a 1 question specifically if there will be. Okay, over to you, Laskar.
Okay. So good morning, good afternoon, and good evening to all of you, and welcome to the 7th WMO International Workshop on Monsoon, IWM-7, and session 24 SP. So our presenters, may I welcome our first presenter, Dr. Sapna Sasane. So already Patnaik sir has informed that about timing and other thing. We can entertain at least 1 question for each presentation if there is any question. So let us start with our first presenter, Dr. Sapna Sasane.
Dr. Sapna, are you there?
So can you, Dr. Busher, can you go to next?
Yes, sir, we are moving.
Okay, so Sanjukta Rani Padi.
Good morning, sir.
Good morning.
So can I start?
Yeah, please.
Good morning, everyone. My name is Samyukta Rani Padi, Senior Research Fellow in Department of Marine Science, Berhampur University, Odisha. My topic is active break cycle of Indian summer monsoon and their variability during cold and warm phase. And objective of the paper, there are 5 objectives. Identify the active break cycle using the IMD daily graded rainfall data for July and August for the core monsoon zone 18 north to 28 north and 65 east to 88 degrees east, to examine the variability in active break for the every 10 days period and every decade during the study period, that is 1901 to 2020, and examine various statistical features of active and break spells during the cold phase, that is first 60 year 1901 to 1960, and the second phase, that is warm phase 1961 to 2020, to understand. And second, next objective is to understand the evolution of active and break spell from the lag 0, -5, -10, -15 and -20 days. We take here for the composite of rainfall, SST, OLR, 10 meter wind, latent heat flux and sensible heat flux. We take here the 0 days, that is the starting of the spell. Starting days of the spell. And the next objective is examine the composite anomaly pattern of rainfall, OLR, SST and surface pressure wind, 10 meter wind during the active and break spell. Next slide. Next slide. Okay. Data and methodology. As I told before that I take the daily graded IMD rainfall data for the whole period, that is 1901 to 2020, and NOAA daily average OISST and OLR for the period 1982 to 2020. As before 1982, the daily data are unavailable, so we take the SST, OLR for 1982 to 2020, and daily mean latent heat flux, sensible heat flux, 10 meter wind from NSEP anchor for the same period before, that is 1982 to 2020. And we divide the whole period 1901 to 2020 into 2 parts, that is cold phase and the warm phase. As shown in figure 3, the SST trend for the 1901 to 1960 in the left panel, and the right panel is 1961 to 2020. And the active brick spell has been identified, followed the paper Rajivan et al. 2010. The period during which the standardized rainfall anomaly is more or less +1 or -1 consecutively for 3 days. We take that is active and break days. We take the core monsoon zone rainfall as Indian summer monsoon rainfall is highly correlate with monsoon rainfall of the core monsoon zone, that is correlation is 0.8. So we take the core monsoon zone rainfall for this study, and my next figure shows the 10 days period of the active break cycle, and the second figure is the right panel, figure 2 right panel shows the decade wise figure. In first figure we can see that active days are first increasing, blue color, active days are first increasing in July and then decreasing in August, which is opposite of to the break days. That is 317 are more in 21st to 31st July, and break days.
Can you go to your summary, please?
Sorry?
Time is over. Time is
Okay.
over. You can
Okay.
go to the summary.
Okay, sir. Okay. In the whole period, we get that we find 193 active spells, from which 106 in cold phase and 87 in warm phase, and 142 in break spell, from where we get 66 in cold phase and 76 in warm phase. Active days spells 3 to 4 days are followed by 5 to 6 days or more as compared to longer days. However, the longer days greater than 11 days are break spells are more than active spells. During cold phase and warm phase, the increasing trend found in active days, while break days shows a decreasing and trend in cold phase and increasing trend in warm phase. Comparison to considering the decadal variability, active days are more during 1941 to 50, and break days are more in 1991 to 2000. During August, number of active days are maximum during 21st to 31st July, and break days are more in 21st to 31st August. After 31st July, decreasing trend observed in active days and increasing other trend are in break days. Thank you, sir.
Yeah, thank you. Any quick question? Only one question we can entertain. No, if there is no any question, so we can go to our next speaker, Dr. Sudeep Kumar BL. Dr. Sudeep Kumar.
Laskar, can you read the name and find out how many are available?
Okay, then Dr. Sudeep Kumar, are you available? Miss Ankita? Dr. Johnny?
Good afternoon, sir.
Okay, okay, so you are okay. So Dr. Johnny?
Yes, sir, I'm available.
Dr. Ramratan?
Yes, sir, I'm available.
Dr. Busher is available. Vikram Raj, Mr. Vikram Raj? No. Mr. Vikram Raj, you are there? Mr. Ashutosh? Miss Nandini?
Yes, sir, I'm here.
Mr. Anandu Rajiv?
Yes, sir.
Miss Manali? Miss Minu R. Nair?
Yes, sir, I'm there.
Miss Basundara? Mr. Subroto Haldar?
Yes, sir.
Miss
I am
Priyanka
here.
Singh?
Yes, sir.
Mr. Venugopal?
Sudeep Kumar, there is chat message. Sudeep Kumar, well, he is available.
Yes, sir. Yes, sir. Yes, sir. I have seen, sir. Only 1, 2, 3, 4, 5, 11, sir. Out of 11, one presentation over. Okay. So we can go to our next presenter, Dr. Sudeep Kumar.
So you can slightly increase the time for them.
Yeah, yeah. Now we can increase.
So shall I start?
Yeah, please.
Okay, sir. So very good morning to all. Myself, I am Sudeep Kumar, and my topic of study is the thermodynamic structure of atmospheric boundary layer of the west coast of India during active and weak phases of Indian summer monsoon. In the literature, we have it has been reported that the thermodynamic structure of the south and northern parts of the west coast is different, and due to that, the cloud structure of this south and north of west coast is different. So, sir, you please keep the first slide only. First slide. Yeah. So the cloud structure is different over south and north parts of the west coast, and it is already literature have shown. But the thermodynamics of atmospheric boundary layer over the west coast is not properly understood due to the lack of very high vertical resolution data sets of this region. So therefore, we try to understand in this study, we try to understand the variation of the thermodynamic structure of the west coast of India during active and weak phases of the Indian summer monsoon. So next slide, please. Yeah. So we used the primary data set we used is the high vertical resolution radio sonar data sets of IMD. So it is available from 2018 onwards only. So at only we have the data set of 0 UTC only. So we used this high vertical resolution data set of radio sonar data set of IMD for our study. And here you can see in the left hand side, that is the profiles of the zonal wind over Trivandrum, Mangalore, and Mumbai, only in the atmospheric boundary layer up to 3,500 meter only. So here you can, this is the important results of our study is that if you compare the wind magnitude, we can see that the minimum wind we can observe over the Mangalore, whereas maximum wind we can observe over Mumbai. Whereas the change, that is difference between active and weak, it is maximum over the Mumbai. And if we see the vertical variation or the vertical profile of the wind, we can see that in the Trivandrum, the maximum wind is of, so the first column, it is the composite profile of active and weak, and the second column, that means the difference between active and weak, and the third is the representative daily profile. And here we can see that in the daily, if you see the daily and composite profile, in Trivandrum, that is maximum wind is above the atmospheric boundary layer, and the wind speed decreases with height while moving towards the ground. That is, there is a sharp increase from the ground towards up to above the atmospheric boundary layer. Whereas in Mangalore, the maximum is within the boundary layer, and in Mumbai, the maximum wind is observed and it is within the atmospheric boundary layer itself. And so that difference, so this different vertical profile makes the instability, or it changes the thermodynamics of the atmospheric boundary layer. So that is evident from the second figure. So that this is the profile of equivalent potential temperature of these three stations, and this profile of equivalent potential temperature. And if we can see that the equivalent potential temperature, if it is decreasing with height, it denotes a conditional instability, and if it is increasing with height, it denotes a conditional stability. So here we can see that in Trivandrum, in the daily profile and composite profile, if we can see compare, we can see that in the lowest or bound, it is nearly conditionally slightly stable. Conditional instability we can see. So that indicates or that is favorable, or indicate presence of stratiform clouds, or it is conducive for presence of stratiform clouds in if favorable dynamic factors are there during active condition. But in weak condition, it is atmospheric boundary layer is conditionally unstable in both active and weak phases. And if you see the vertical profile in Mumbai, it is almost neutral, or means slightly uniform due to the well convective mixing in Mumbai. It is we can see that almost uniform up to around 1000, or in the low boundary layer it is almost neutral, so that indicates high convective mixing in the Mumbai. So the summary is that due to this vertical profile variation in the vertical profile of wind, so that mainly influences the thermodynamic structure, and we can see so that indicates or favorable for the stratiform kind of clouds in the southern parts, and vertically developed clouds over the Mumbai. Study we could identify the different thermodynamic structure of this south, central, and parts of the west coast. So that's all. Thank you.
Okay, thank you. Any question? No. So thank you very much, Dr. Sudeep.
Thank you, sir.
So next presenter will be Miss Ankita.
Yes, sir. Good morning.
Good morning, please.
So may I start?
Yes, please.
Okay, thank you. So I'm Ankita Katoj. I'm from Jawaharlal Nehru University, and today my topic is wet scavenging of heavy metals during monsoon in Delhi. So the objectives of this study are to assess the heavy metal concentrations in rainfall in Delhi during monsoon months of July and August in 2021, and to determine the relative abundance and interactions of heavy metals which are toxic to human health and are contributed by anthropogenic sources. Next slide, please. So for methodology, the heavy metals are scavenged during rainfall, and therefore the atmospheric deposition of heavy metals is an important marker of precipitation chemistry. In this study, the rainfall samples were collected at JNU itself. The coordinates of this site are 28° north and 77° east. JNU has a very high green cover, and it has a total campus area of 4.12 kilometers square. So the samples were collected using sampling assembly of bottle and funnel of diameter 20 centimeter, as shown in the figure. Samples were digested after collection using 1 milliliter of 5% nitric acid and were preserved for at 4 degrees Celsius for analysis. The prepared samples along with the blanks were analyzed using ICP OES, and the samples were analyzed quantitatively using multi-element standard. Next slide, please. So for the results and summary, the figure 3 shows the relative abundance of heavy metals during rainfall events, whereas the figure 4 shows a matrix showing the interactions between heavy metals and rainfall depth. Next slide, please. The important results were that it was observed that among all the estimated metals, aluminium showed the highest mean concentrations of about 1059.2 microgram per liters. The concentrations of this lithogenic metal ranged from 0 to 5,180 microgram per liter during the months of July and August. But this metal is of crustal origin. It can also be anthropogenic, but as well as crustal. Among the heavy metals which are primarily contributed by anthropogenic sources, lead, nickel, and chromium were the most abundant metals at the selected site. The Pearson's correlation coefficient in the previous figure showed good association between nickel and chromium, which indicated common sources such as fuel combustion. As for the crustal elements, good correlations were observed for aluminium and iron, aluminium and barium, and iron, which showed their origin from mineral ores in the dust. Negative association between rainfall depth and heavy metals indicated the scavenging effect of rainfall on heavy metals. Thank you.
Okay, thank you. Any question?
I just have one question.
Yeah, please.
I just want to know, like, how many samples were collected and what was the duration?
Sir, the samples were collected during July and August, and the number of rain events that we could collect were about 15.
Just one season or spread across different seasons?
No, sir, it was only for 2021, so only 15 samples.
Yeah, okay, thank you.
Thank you, sir.
Any other question from anyone? No. Okay. Thank you, Ms. Ankita.
Thank you, sir.
Next presenter is Dr. Joni.
Good morning.
Good morning. Please start.
In this work, I am analyzing the performance of the GFS and GFS model, which is operationally running at IMD. So IMD is routinely providing the forecast in the medium range scale using the global forecast system and 21 determining system and 21 member global ensemble forecast system. Both the models are running at a T1534 resolution. So here we evaluated the rainfall forecast of the GFS and GFS model during the southwest monsoon period from June to September, and it is over the Indian region, and we have studied it is over the different spatial domains, different homogeneous regions of the IMD, and we have studied also model forecast in the prediction of the extreme rainfall event. So this rainfall is verified, model forecasts are verified against the IMD graded rainfall data, which is combining the rain gauge observation and satellite rainfall. And extreme rainfall events, for studying the extreme rainfall event, we used our IMD synoptic station rainfall observation. And here this is a mean error in the GFS and GFS model for the June, July, August JJS period. So it is observed that individually, if you are looking for the June, July, August, September month separately also, over the land region of the west coast, there is a underestimation of the rainfall, and northeast region there is a overestimation of the rainfall, and the land sea region of the west coast also there is an overestimation of the rainfall. And for comparing the extreme rainfall event, since we are comparing the model rainfall with the station observation, we considered the maximum rainfall occurring in the 0.5 degree around the model station location in the model forecast. We considered for the comparing with the synoptic observation, synoptic session observation. So here we are saying the what percentage of the observed rainfall model was able to predict in different rainfall category. So extreme, here we selected only the extreme rainfall observation, that is above 20 centimeter, and we found that at what percentage of this rainfall is predicted by the model in different categories. So the first top panel is the GFS model, and bottom panel is the GFS ensemble mean. So we found that only 10% of the heavy rainfall events, only extreme rainfall event only, model was able to predict in the extreme rainfall category, and 25% it is able to predict in the very heavy rainfall category, and almost 85% of the model was able to predict in the heavy rainfall or above category, that is 6 centimeter and above rainfall category. So this picture is for South Peninsula, and we have done it for the Northwest India, Central India, and Eastern Northeast India. So we almost 85% of this extreme rainfall event model was able to predict in heavy rainfall or above category on the South Peninsula, Northeast, Eastern Northeast India, and Central India. And Central Northwest India, that it was around 60% in Day-1 forecast. And if you are going for the longer lead time, it is percentage is decreasing. So I'm summarizing the result. There is an overall underestimation of the rainfall over land region of the west coast of India, and overestimation in the northeast of India, and there is an overall underestimation of the extreme rainfall event in both the models. And GFS model was forecasted 80%, 85% of the observed extreme rainfall event in heavy rainfall or above category in South Peninsula, Central India, and East and Northeast India in their Day-1 forecast. Thank you.
Okay, thank you. Any question? Dr. Joni?
Yes, sir.
So in summary, you have written there is an underestimation of rainfall over land region of west coast of India and overestimation of rainfall over northeast region.
Yes.
In both the models. What could be the reason according to you?
Exactly, I don't know the result. So there, maybe if you are including the land data assimilation system, those things it can improve. And generally, there is a dry bias is observed by most of the models over the Indian region. So exactly, I cannot tell the answer.
Okay, thank you. Any other question? Okay, so we can go to our next presenter, Dr. Ramratan.
Hello.
Yeah, please.
This is Dr. Amratan. Currently, I'm working as a senior manager in climate connect technology, and this work is done when I was working as a project scientist in IMD Pune before joining this organization. And this work is mainly wind power potential assessment of India using IMDA and ERA5 reanalysis data. Now, as we know that like renewable energy, it's clean energy and very less energy, it's very less amount of pollution generated when we are using renewable energy. So the objective of this work is to compare and contrast the wind power potential of India using IMDA and ERA5 reanalysis data set. So basically, we want to check that our NCMWF reanalysis data, how much it's better or worse compared to ERA5. Okay, so basically we're comparing to reanalysis data. Okay, so the data which we have used for this study is like IMDA and ERA5, and IMDA data we know that the resolution is around 0.12 into 0.12 degree. This and temperature resolution is 3 hourly. And ERA5 is like almost 0.25 to 0.5 degree spatial resolution, but it is in early estimates. Okay, so we have taken data from 1985 to 2019. So roughly 35 years of data we have taken. Okay, can you go to next slide, sir? Yeah. So the methodology which we use is wind speed is calculated from U and V wind at 1000 HPA level. So square root of U square plus V square, if you do, that will give us wind speed. And from this wind speed, the power we calculate using half rho A capital V cube. So in this one, the power is directly proportional to the area of wind turbine, and it is like third power of wind velocity. Okay, so that means if we are having a error of 2 in getting wind velocity wrong, that means in the power we are getting 8 times like power wrong. So if we calculate it WPD, that is power per unit area, that will be half rho V cube. So again, it's proportional to power 3 of wind velocity. So we have taken both these data set, and if you see this figure 1, it is wind power potential. Sorry, I have written it as wind speed. It's wind power potential. So the color code in this one, the darkest color is around 500 wind power potential, wind power density, and the lowest is around 0. So more than 100 to 150, it can be harvested, or roughly 200 if it is like mean for yearly, that can be harvested. So what we can see is throughout the, like this is just I'm showing for 4 months, so JJS month. So what we can see that the upper part in this one is B is for July. So for July, we can get the maximum wind potential from IMDA and ERA5, both these data sets. Okay. And then if we calculate the monthly wind speed departure between IMDA and ERA, so what I've done is IMDA minus ERA divided by ERA in percentage term. So the red curve is the red part in the spatial pattern in the figure 2 is the reason where IMDA is overestimating the wind power potential. Okay, and the blue is where it's underestimating. So now since both are reanalysis data, so we can't say which data is better. So for that, we got observational data from National Institute of Wind Energy for 2 locations, the one over Tuticorin and the other over Kanyakumari. For these 2 stations, in the figure 3, you can see that in this one, we have used IMDA for these point location, ERA5 for that point location, and the observation data. So what we can see is that the red curve, which is that red and blue curve. So IMDA and ERA, they are quite nearby throughout the like in the monsoon season, pre-monsoon season, as well as in the post-monsoon season. The same we can see in the next part also, Kanyakumari also, like blue and red, they are nearby. So effectively what we got is that our state-of-art IMDA data, it is good compared to the observational part. So compared to ERA 5. So since ERA 5 is widely used in the global in many parts of the world for these analyses. So what we find is that our IMDA data is also very good and that we can use for many purposes. So like here I'm using it for wind speed. So the conclusion of this overall is that higher wind speeds are observed in the western state of Gujarat and Rajasthan from both IMDA and ERA 5 data sets. And the wind speed is found to be maximum in the month of monsoon months, and it is in the monsoon months also it's maximum in the July part. And the seasonal pattern of wind power density matches in both IMDA and ERA 5 data sets. And IMDA overall overestimate the wind power potential as well the wind speed compared to ERA 5. And also if we see, if we compare it with the observational part, what we can see, as I already mentioned, that IMDA is very much matching with the observational part. So these are the basic conclusion which we have drawn from this study. So thank you very much, and if there is any question, I will be happy.
Thank you. Any question? No. Okay. Thank you, Dr. Ramratan.
Thank you.
Okay. So we can go to our next presenter, Dr. Busher.
So good morning all. So the title of my presentation is Extended Range Forecast of Onset of Southwest Monsoon over India using Coupled Model. So in this presentation, I am discussing about the operational capability of real-time forecast of onset of Indian monsoon in the extended range. So for this purpose, I have used the extended range forecast that is operational at India Meteorological Department, and I have used 17 years of data from 2003 to 2019 for the analysis. Next slide. So this is the left top figure shows the structure of the IMD's operational extended range forecast system. So as of now, we are having 16 ensemble members, which runs for 32 days in every week. For these studies, I have used the parameters I have used is the rainfall averaged over near to the Kerala coast in the Arabian Sea, and the zonal wind at 850 HPA wind averaged over the Arabian Sea region, and the zonal wind at 600 HPA. So the condition I have used is that if the rainfall average exceeds the 80% of their mean, and zonal wind at 850 HPA, if it exceeds the 70% of their mean, and the zonal wind if it exceeds 0, which means when it converts to westerly. So on that day, I consider as an onset of monsoon, and another condition is that if all three conditions is satisfied for consecutive 5 days, then the first day is considered as the onset of the monsoon. So for these purposes, I have used the initial condition of the 15th May, and I did analysis for 17 years. The right top figure shows the evolution of the onset of the monsoon, and the predicted and observed onset I have tabled here. If you look into the table, we can see the green color I have shown is that the is showing if the predicted one is closely matching with the observed one. So in the summary, I have the result indicates that the real-time ERF has the capability to predict onset of monsoon objectively about 2 to 3 weeks in advance. So from the result, about 77% of the cases are closely matches with the observed dates on the onset of monsoon over Kerala. Thank you.
Okay, thank you, Dr. Busher. Any question from anyone?
Yeah, Laskar, I have one thing.
Sir, please, sir.
Okay, Busher, so this color, what is the color? Yellow and green, red means.
So this green color shows that if the observed and predicted one is closely matching with if the predicted one is closely matching with the observed one, that is plus or minus 3. If the deviation is plus or minus 3, it is mentioned in the green color, and if it is plus or minus 4, it is in the yellow, and if it is higher than 4, then it is represented in the red color. So from the result, what we have seen is that the 77% of the cases are coming under the green color.
3:30 से 4 बीच में होगा.
Okay, any question?
हाँ,
Any other?
delay नहीं है.
Sir, Patnaik sir, you got the answer?
Yes sir, yes sir. Yeah, I got it. हाँ, ठीक है.
So any other question? Dr. Busher?
Yes, sir.
Just I want to know that in the year 2003 and 2010.
Yes, sir.
What was the reason? Have you gone through any reason? Or was there any pre-monsoon activity or anything that our deviation was 9 and 11 days respectively for those 2 years?
Sir, the thing is that in 2003 and 2003 there was some if you look at pre-monsoon activity was the rainfall activity was there. So and similarly the westerly winds was also in 600 HP also wind speed was westerly, wind was westerlies that we observed in the 2003. So some odd cases are there. So in like 2003 and 2010 and 2016 and 2000.
Can I add to his answer?
Yes,
Actually,
sir.
I remember 2003 because it was delayed. There is influence of cyclone, particularly over the Bay of Bengal during that period.
Okay, that's what I wanted to.
It was recurve. So that has actually caused the delay. But probably the model could give the rainfall. So it was not able to detect whether it is monsoon or some cyclone influence. That may be the reason. Actually, these are the year where it is not matching. We need to examine more detail.
Yes,
Okay, Busser, you can do that one also. The red things, na? You
Yes,
can
sir.
basically see where it has failed. So reason we can find out.
Okay, sir. That we'll do that. We'll study. We'll extend the study.
Yeah, thank you.
Thank you, Dr. Busher. So we can go to our next presenter. Whether Dr. Vikram Raj is available? No. Dr. Ashutosh? No. So our next presenter will be Miss Nandini. Yeah, please. Please start.
Good morning. I'm Nandini. I'm currently doing PhD in IIT Bhubaneswar. So today I'm going to present our work on the amplification of Arabian Sea aerosol monsoon relationship during El Nino. So the main objective of the work was to explore how the relationship between aerosol loading over Arabian Sea and central rainfall is changing during different phases of ENSO, and to analyze if there is any regional selectivity in the dust-induced rainfall enhancement. Next. So it was observed that on weekly timescales, there exists a positive correlation between aerosol loading over Arabian Sea and central Indian rainfall, which is mainly attributed to the desert dust aerosols, which is being transported from the West Asian deserts. And it is known that both the emission and transport of dust from the West Asian deserts and the rainfall in India is modulated by the large-scale oscillation ENSO. So next. So we analyzed how the rainfall over India and aerosol loading our Arabian Sea is changing during different phases of ENSO. So during El Nino, we know that India is generally receiving deficit rainfall. So at that time, the aerosol loading our Arabian Sea was found to be higher. And during La Nina, when there is a surplus rainfall over India, both the AOD and AI values of Arabian Sea was found to be comparatively lower. So basically, having contrasting effect on the aerosol loading over Arabian Sea and the central Indian rainfall. So chances are there that the observed correlation between the AOD or Arabian Sea and central Indian rainfall weaken when these large-scale oscillations are prominent over India. Next. But interestingly, it was observed that the correlation exists and is significant during all phases of ENSO. And the correlation is basically following the aerosol loading conditions over Arabian Sea, with the highest correlation observed during El Nino, followed by Normal and La Nina. So it is clear that whenever there is an enhancement in the aerosol loading over Arabian Sea, there is an enhancement in rainfall, which is basically leading to the strengthening of the observed correlation. Next. So we analyzed how the during high aerosol loading condition, the wind speed is changing over Arabian Sea. So contours are showing the climatological wind speed, which the high winds over Arabian Sea, which is generally concentrated around 5 to 15 degree north and 50 to 60 degree east, was found to be shifting northeastward towards Indian region during high aerosol loading condition. The color bars are showing anomalies during high AOD. Next. And this shift towards Indian main at us in enhancing the moisture transport, and it can be seen that the enhanced moisture transport is widespread across the Arabian Sea and the Central Indian region. Next. And this shifting of winds and the enhanced moisture transport over Arabian Sea is thereby leading to an increased rainfall. So many studies have been showing different regions where this dust-induced rainfall enhancement is more. So it is clear that the dust-induced rainfall, and there is widespread increase all over India, and the highest enhancement is observed over Central India, Northwest region, and along the Western Ghats region. Next. So it is clear that the correlation between aerosol loading over Arabian Sea and Central Indian rainfall exists and is robust during all phases of ENSO, and there is no specific regional selectivity in the dust-induced rainfall enhancement. We clearly see that there is widespread increase over India, with largest enhancement over the North, Northwest, and Central Indian region. And in the future warming scenarios, it is expected that the El Nino-like conditions and the emission and transport of dust towards the Arabian Sea from the West Asian deserts are likely to increase, which makes this dust-induced rainfall enhancement more significant. Thank you.
Okay, thank you.
I have
any question?
Yeah, I have one question.
Yeah, please, sir.
Okay. So this is very interesting, that aerosol loading influencing monsoon rainfall over central India.
Okay.
Do you have any
Yes,
particular year that has happened strongly?
No, like we haven't analyzed in separately for years. This analysis we have done for the period 1981 to 2013. So this is already established actually that this positive correlation
I am interested to know that 2009 case. 2009
Okay.
June, it was many papers indicate. So whether you have analyzed that event, that was my main purpose.
No, sir, we haven't analyzed separately. We will look into it actually. Thank you for looking.
Thank you.
Any other question from anyone else? No. Okay, thank you, Ms. Nandini.
Thank you, sir.
So we can go to our next presenter, Mr. Anandu Rajiv.
Hi, sir.
Yeah, please.
Good morning, everyone. I'm myself Anandu Rajiv, and I'm doing. I'm working as a research fellow in the Indian Institute of Technology, Webster. So today, my presentation is on the long-term trend in rainfall during various seasons, like a case study over India. So we all know that the rainfall occurring over India is in the recent times. So how this rainfall is changing and how this extreme rainfall is changing over time is critical for agricultural planning as well as business mitigation. So our objective of this paper is to explore the long-term trend in rainfall during various seasons like pre-monsoon, monsoon, and post-monsoon seasons. Also to find out how extreme rainfall is contributing to this changing rainfall pattern, and also to locate the regions which is having a significant change in rainfall as well as extreme rainfall. So, so first we looked at how rainfall is changing in a long time. Like we have taken the data from 1917 and 2019 IMD rainfall data. And from here, like in the long-term trend in rainfall data and how the contribution of this rainfall to annual mean is changing, we look at it. So we can find out that during the pre-monsoon season, the southern India is, and when we look at the contribution also, we can see, found out that this change is actually significant over the southern region during the pre-monsoon season. And when we looked at the monsoon season, we can find out that the northwest region as well as the west coast is showing more predominant change in the rainfall as well as the extreme rainfall as well. So when we looked at the post-monsoon season, like in the east coast, mostly like the Odisha and Kolkata region are showing increase in the rainfall pattern, and as well as like that the contribution of rainfall to annual mean also we can see that there is an increase. And so how extreme rainfall is contributing to this? So we looked at extreme rainfall. So to find out the extreme rainfall, we used like 95%. So whenever the rainfall is more than 90%, we consider as extreme rainfall. So we looked at the trend of how extreme rainfall is changing. Also like how extreme rainfall contribution to total rainfall is changing for the same time period of 1979 to 2019. So we can see here we can see that the extreme rainfall is showing a similar pattern as that of the rainfall pattern, that the region like in the post-monsoon and the pre-monsoon season, the southern India which is showing a increasing trend in the rainfall pattern, also showing an increasing trend in the extreme rainfall. like in the also the west coast and northwest region, also showing an increasing trend during the monsoon season. And in the east coast, mainly Odisha and Kolkata region is showing an increasing trend in the extreme rain. So now, like how these extreme days are to look at it, we found out that the days which is greater than 90, days which is having rainfall greater than 90%, we considered it as extreme day, and we plotted it for like different seasons, like pre-monsoon, monsoon, and post-monsoon. So here also we can see that this is also having a similar signature as that of the rainfall patterns. Like during the pre-monsoon season, the southern India is showing an increasing trend, and in monsoon season, the west coast is showing an increasing trend, and during the post-monsoon season, the east coast, mostly Odisha and Kolkata region, is showing an increasing trend. So in the summary, we found out that the trends are like temporary and especially heterogeneous, and regions which is showing a significant increase in rainfall pattern during various seasons is also showing a similar trend in extreme rainfall as well. Also, when we looked at the extreme days, we found out that it is also shows a similar pattern as that of extreme rainfall. That is the region which is having higher rain rate also has more number of extreme days. That's it. Thank you. Hello.
Okay, yeah. Thank you very much.
Thank you.
Any question from anyone? No. Okay. Thank you, Dr. Rajiv.
Thank you.
Okay, next we can go to Miss Manali. Please.
Good afternoon, everyone. I'm Manali Shah from Indian Institute of Remote Sensing, ISRO, Dehradun. And the title of my work is Evaluation of the Indian Summer Monsoon Under the Influence of Climate Change. And the objective of the paper is evaluation of the numerical models in capturing the structure of Indian summer monsoon during the historical time period and investigation of changes in the ISM system due to variable warming. Next slide, please. Okay, the data I have used in this study is ERA 5 reanalysis sea surface temperature and precipitation data with a special resolution of 0.25 degree to cross 0.25 degree for the study period of 1980 to 2014, which is of 35 years, and the SIMIP6 climate historical simulation data from 1980 to 2014, 35 years of data, and future warming scenario data, which is socioeconomic pathway 245 from 2065 to 2100. And the methodology is that we will take the climate model output for warming scenarios, and we will see the future warming experiment SSV 245 and see the special plateau and the statistical significance, and go for the final results and conclusion. The Taylor diagram analysis of sea surface temperature shows that in the Arabian Sea, it is showing the correlation of almost 0.8 and the precipitation of around 0.5, which is thus we can see the for the 12 climate couple models, we can say that these models are able to capture the Indian summer monsoon. So we will go for the future simulation. And for the spatial distribution of precipitation, we can see that the models are giving us a trend, increasing trend of the rainfall for northeastern Himalayas region and the Western Ghat region. And all of the models almost capture the same phenomenon, and the black stipples are showing the significant location of the changes at 95% confidence interval. And the apart from a few models like NESM3 and CSM2 WSECM, almost all the model captured the strengthening of the rainfall at Western Ghats and Northeastern Himalayas. So I'll derive some important conclusion from the study, that the comparison of the semistic model considered in the study with the observational data shows ERA 5 positive correlation of the order of 0.7. And in the context of future warming scenarios, most of the models show significant trend of summer monsoon rainfall over the Western Ghats and the Northeastern Himalayas, and therefore the analysis of the Indian summer monsoon shows insignificant change in the backdrop of global warming and future warming scenarios. Thank you so much.
Okay, thank you. Any question from anyone? No. Okay. Thank you, Miss Manali.
Thank you, sir. Thank you, sir.
We can go to our next presenter, Miss Minu. Miss Minu.
Yes, sir.
Please.
Good afternoon, all. I'm Meenu and I am presently working as a JRF at IITM Pune. Today I'm going to present observational atmospheric vertical structure of a core monsoon zone in central India. Our objective is to study the vertical structure of turbulence over Bhopal, which is located in a core monsoon zone in central India. For the study, we use 10 years of GPSRS radio sonde data. And we know that the monsoon core zone is characterized by the intra-seasonal monsoon variation of active and break. So in this study, we explore differences in VST and other parameters during active and break phases of monsoon. Next slide, please. So for studying turbulence, we use a parameter called CN square, which is called refractive index structure parameters, which is dependent on the temperature, humidity, and pressure profile in the atmosphere. The figure shows, the color plot shows the VST using daily mean climatology over Bhopal, and we can see that there exists a high time and height variation of CN square with higher values at the surface. The higher values at the surface is can be attributed to the planetary boundary layer, and it's a planetary boundary layer. And we can see that there exists a clear transition between monsoon and non-monsoon months. The region between the two red lines shows a monsoon season, and we can see that there's a clear difference between monsoon and non-monsoon months. The most important feature is the presence of a weakest turbulence zone, which is centered at around 14 kilometers. And we can see that even before the monsoon onset, it started occurring. And this weakest turbulence zone is conspicuously seen only during the monsoon season. And also at lower heights, we can see that there is an elevated levels of higher turbulence values, even up to 7 kilometers. And the other notable feature is the presence of a secondary maximum between 17 and 20 kilometers. And we can see that it persists throughout the year. This the turbulence is mainly due to the presence of thermodynamic and dynamic features. And this feature at 17 to 20 kilometers due to the presence of dynamic features, that is, during the non-monsoon months, it is due to the upper flange of subtropical westerlies, and during the monsoon months, it is due to the presence of lower flange of tropical easterlies. So we know that the monsoon is characterized by the wind reversal. So the dynamic factor is responsible for the secondary maximum layer between 17 and 20. And the weakest turbulence zone, which is centered at around 14 kilometers, is due to the presence of higher cold cloud fractions around that height. And we notice that the monsoon season is more homogeneous in nature compared to the other season. So to further explore more about the intra-seasonal variation of monsoon, we have studied the active and break days. With active, we have analyzed 174 active and 78 break days, and we notice that there exists differences of turbulence between active and break. With the first noticeable difference is around this weakest turbulence zone at 14 kilometers, and also below that height we can see the difference in active and break phase. With below 5 kilometers, there is during active phase there is increased turbulence, and the other height we can see the turbulence is lower than active phase. So this particular vertical structure is mainly affected by the gradient in relative humidity, temperature, and dynamic features. So further looking into the more features, the second plot in the lower panel shows the fractional cloud cover obtained from reanalysis data, and we can see that there is a clear difference between active and break cloud cover, with active region showing more cloud cover compared to break. And this difference in cloud cover at 14 kilometers, that is higher cold cloud fraction, is responsible for the difference in turbulence at this height. And at the lower heights, we can the third plot shows the gradient in bold line shows a gradient in relative humidity, and the other just relative humidity. And we can see that there is a clear difference between active and break phase relative humidity gradients. And this feature combined with the difference in difference in gradient in temperature is responsible for the particularly observed VST during active and break. Next slide, please.
Yeah. So this is your left. Okay. Thank you.
Next
Thank
slide.
you. So any question?
See, Terry, next slide. Do you have any?
No, rest I,
Yeah,
oh,
this
rest I,
is a summary of the
okay.
yeah.
Okay. Continue, please.
Yeah, so summarize, we can see that the CN square profile values are from the range of -18 to -12, meter raised to -2/3, and we can see that the early signature of weakest turbulent band is noticed even before the onset of monsoon, and monsoon season VST seem to be more homogeneous, and the higher cold cloud fraction is responsible for the weak turbulent zone, and active and break show significant differences in CN square profile, and the strong thermodynamic and dynamic factors are responsible for the observed VST. Thank you.
Okay, thank you. Okay, thank you. Any question? No. So if there is no question, thank you, Miss Men.
Yes, sir. Thank you.
So our next presenter is Miss Basundhara. He is available. No. Mr. Subrato Haldar.
Yes, sir. Let me share the screen.
Okay. It is not with admin.
No, sir. Good afternoon, everyone. I am Subrata Haldar, PhD scholar from Indian Institute of Tropical Meteorology. I am going to present the study on decadal variability of monsoon core zone rainfall. And our objective of the paper is to study the decadal variability of monsoon core zone rainfall and its association with sea surface temperature variability. And the observation data used are ERSST version 5. Precipitation data are used University of Delaware, GPCC, and IMD 0.25 by 0.25 degree. And here techniques are used: spectrum analysis, wavelet analysis, bandpass filter, correlation, and composite analysis. Here we can see from IMD dataset the filtered standard deviation of rainfall, and we can see it is more over the Western Ghat, and after that over the monsoon core zone region. So we have shown this variability of Western Ghat rainfall in our previous paper, and now we are going to discuss about the variability of monsoon core zone rainfall in decadal time scale. So here is the 31-year running correlation of filtered monsoon core zone index with different filtered SST indices. And here we can see the throughout the time period the relation between the monsoon core zone rainfall and the other SST global SST indices is changed throughout the time period. And the most prominent change is the interdecadal precipic oscillation and the Nino 3.4 SST, which was negative through 1901 to 1948. And it is in recent period the relation is positive. And so we went with the composite analysis of summer monsoon sea surface temperature during summer monsoon. So and here we can see that during period 1 the IPO and IPO was negatively related with the monsoon core zone rainfall, and after that in the second period the relation is reduced, and in recent period the relation is more prominent and the relation is positive with monsoon core zone region. And in the second period here, we can see that tropical Indian Ocean sea surface temperature, that basin mode variability is positively correlated with the monsoon core zone rainfall. And our conclusion is that decadal variability in rainfall over the MCZ display time varying relationship with dominant SST mode. And also from the dynamical and thermodynamical processes study, we have observed that during period 1, the dynamical processes was more related with the monsoon core zone rainfall variability, and during second and third period, the monsoon related moist thermodynamics was responsible for this variability. And for future study, for detailed mechanism of this variability, we have to go for coupled modeling. Thank you.
Okay, thank you. Any question? No. Okay, thank you, Mr. Subrato.
Thank you, sir.
Our next presenter is Miss Priyanka.
Thank you so much, sir. Kushal, could you please zoom in, please? Sir, am I audible?
Yes, yes.
Okay. Sir, Kushal, could you please zoom in slightly? Thank you. So, sir, today I'm going to present my work, which is block level weather forecast based agro advisory and its impact for Bihar. So, in the present work, rainfall forecast of GFST 1534 model, which is available at 12.5 kilometer resolution, process at block level is verified with block level observation of East Champaran, Nalanda, and Supaul district of Bihar for monsoon 2020 and 21. So why we have selected these three districts only? Because these three districts belong to three agroclimatic zone of Bihar, where ACZ is the zonation, where the area has been divided on the basis of climate, soil, agricultural practices, and crop grown. So the study on these three areas only could be able to represent the agriculture scenario of Bihar. So the further after the verification, we have studied the impact of weather forecast based AAS, which is Agromet Advisory Services, which are provided under the GKMS scheme of IMD. So, and what is the impact of these services in these three districts as well as in the Bihar? So under the GKMS scheme, as we know, based on the 5 days weather forecast, we provide the Agromet advisory for the farmers of about all the districts of Bihar and almost all the districts of Bihar, all the blocks also we are covering. So once we go to the data part, the data I have used in the study is the 12.5 kilometer resolution forecast provided by IMD, which is GFST 1534 model forecast. And the observed data I have collected from the Bihar government, which is block level AWS data procured on observed under the Meghdut scheme of government of Bihar. The feedback study I have conducted with the help of the units. We have a network of 12 units in the Bihar. With the help of these units, I have conducted the feedback study for the AS services as well as the weather forecast provided. So for the methodology part, the verification has been done based on the standard method recommended by WWRP-WGEN, which is a 2x2 contingency table. And I have calculated ratio score, the probability of detection, HK score, as well as the false alarm ratio for these three district forecasts. For the representation purpose of the verification part, what I have done here, I have divided the 65 blocks in the percent area. As we can see in the graph, in case of ratio score, I have also categorized the scale which is a 0 to 1 into 3 score. Low is less than 0.5, medium is 0.5 to 0.75, and high is more than 0.75. As we can see, in case of ratio score, 75 to 85% of the area, that is 65 block, falls under the medium score. 10 to 15% of the area falls in the low, where whereas 5 to 10% area indicates the high percent of the high skill score for the ratio score. We can also see here the performance of monsoon 2020 forecast is slightly better than that of the monsoon 2021 forecast. And also as we move towards the day 1 to day 5 up to day 3, we have the good agreement of forecast, whereas it's slightly less than in that of the day 4 and day 5 case. When we come to the HK score, the medium, that is 65 to 80% of the area falls in the medium category, that is less than 0.25, and more than 0.25, we have 5 to 25% of the area. In that case also, the performance of 2020 is better than that of the 21 forecast. Similarly, for POD, we have found that 90 to 95% of the area have the high POD score, that is more than 75%, and 50 to 75% we found in 0 to 5% of the area. So in case of the PAD, we found that we have a good agreement of forecast verification. And for FAR, we have 5 to 10% of the area in the low category, which is more than 0.5. Medium, we have 70 to 90%, which is 0.3 to 0.5. And in case of high, that is less than 0.3, we have 10 to 15% of the area. So in all these scores, we have we also found that the forecast score of 2020 is performing slightly better than that of the 21 forecast. So spatial verification, I have also tried to do. In that case, I have found that though more than 60 means we found more than 60% of the ratio score in almost all the blocks. But in case of 2 blocks of Nalanda and 1 block of Champaran, which is Ekargarai and Asthavan, and in case of Star Champaran, it is Pipra Kothi, the performance is quite low. And I have found with the local sources that in case of these 2 districts, because of the local activity, the rainfall occurs sometimes. And in case of Pipra Kothi, there was a problem in AWS. So we in and all, we found that the ratio score is almost 60% for almost all the blocks. Similarly, HK score is also performing well, except these 3 points which I have already mentioned. So further, this feedback study. So we have conducted 2 types of feedback here: dynamic feedback, which we used to take after in weekly interval by almost all the units. They targeted 30 farmers of their area and took the weekly feedback from these farmers based on their AS performance as well as the forecast performance. So, and in the case of monsoon 2020, in the end of monsoon 2020, we have performed the end of season feedback also for about 100 farmers. So this is my summary. The forecast part I have already covered, and we have found that accuracy of the forecast were found good up to 3 days and subsequently decreasing. However, in the bi-weekly agromet advisory, what we do, we update the advisory on every Tuesday and Friday. So being updated on every 3 days, the good accuracy forecast only came into the picture. And in case of block level analysis of the forecast, I have already discussed these 3 points were the problematic point, and which has been already discussed. And once we came to the feedback analysis, it indicates that advisories are highly useful for the farmers, and they follow the advisory particularly for sowing, irrigation, fertilizer application, and harvesting operation. Prior information of rainfall and extreme event emergence, extreme events are significant requirement of the farmers, and more than 70% of the farmers are satisfied with the forecast. So there is one more thing, that I have performed the categorical quantitative forecast verification also, and it is found that the model is not able to capture the high rainfall event. And in case of the feedback, we have found that most of the farmers are required the information of high rainfall forecast only. So this is the gap area which I have found, that we have to work upon these things also. So where we can use the now cost product and other products to meet the farmers' requirement. So this is all from my study, sir. Thank you so much.
Thank you, Ms. Priyanka. Any question? Yes. Ms. Priyanka, I want to know that whether you have considered any manual observatory or all AWS data only.
Sir, in this case, I have considered the AWS only.
So these are quality checked data? Or?
Yes, sir. Yes, sir.
Any question from anyone? So, thank you.
Thank you, sir.
Next presenter, Mr. Benugopal, whether he is present. Mr. Benugopal? No. Dr. Sapana Sasane? No. Mr. Bikram Raj? Mr. Ashutosh? Okay. So with this, we came to an end of this session, poster and short oral presentation. Thank you very much. Thanks to all.
Hello, sir.
Yes.
I am Vasundhara Balde. My presentation is remaining.
But you didn't respond.
21.
Okay, please start.
ID number 21, sir.
Yeah. Dr. Busher, do you have your presentation? Yeah, please.
Hello. Today's the topic of my presentation is projection of Indian monsoon sparse zone shift under climate change. The identify the monsoon sparse zone, track its shift, and to provide the future projection for it. Then the data. The daily rainfall data for 116 years from 1901 to 2016. Data is also used, and to identify the monsoon sparse zone at the Met calculated the rainfall for each meteorological subdivision, and after that I divide the rainfall years into excess normal year and negative normal year. Based on that, I have of excess rainfall year and the number of positive normal rainfall years are less than the deficit rainfall year, and the number of negative then the meteorological subdivision experience lesser rainfall than its long-term mean. When three or more than sub come under category, which are shown in the flow chart, then that region is called as term. It is found that the Indian summer monsoon variability is important for social aspect as well as. So earlier temporal variability of Indian summer monsoon rainfall has been studied extensively. However, the spatio-temporal variability of area is getting less attention. For that, monsoon sparse zone is give the information where to completely observed when there is a monsoon sparse zone, the number of deficit rainfall year. So the with term that region as the MSZ, monsoon sparse zone. The MSZ shows the shift to India in the past century. After that, the 21 years running correlation is also checked. For SST, Arabian Sea SST, it is found that the Pacific Decadal Oscillation SST and strong negative correlation with MSZ locals. For the future projection, I use Cordex for equidistant used for direction. Multimodal ensemble is standardized precipitation anomaly and standardized precipitation evapotranspiration index is calculated, and based on that area is calculated using cluster analysis, and the future track of the MSE is calculated. Continue its counter shift in future also. It will be shifted from the central East India to the northwest India. Summary and the conclusion for my presentation is the monsoon sparse zone is important area in India. It has shown counterclockwise shift in a past century over India, and it will be continue its shift in to counter their future. So the northwest India is likely to more prone to form the droughts in a. Thank you, sir.
Thank you. Any question? No. Thank you, Ms. Vasundhara. So, anyone left out? Dr. Sapna, Mr. Vikram Raj, Mr. Ashutosh, Mr. Venugopal? No. Thank you. Thanks to all the presenters for nicely presenting and completing within time. So now over to Patnaik, sir.
Yeah, I'm really very thankful to Dr. Laskar kindly, because just see, we are just finishing in time, so that is more important. And okay, few were missing, but overall we have got good number of presentation, and 16 presentation, it is good. And those who could not make presentation, there is a PDF and video will be available if they have submitted. Or if today somebody has missed, like to present tomorrow also, there can be some missing person tomorrow, so that we can also will explore if you convey it in well in advance. So with this thing, we are this forenoon session today we are closing, and thank to all the chair Dr. Raskar and all the speakers. So we will again reassemble at hall A for the invited talk in the afternoon session, that is at 6 p.m. That is our 12:30 UTC. Till that time, bye for now. Thank you very much.
Thank you. Thank you, sir. Thank you, everybody.